I'm pretty sure I would be able to carry that box. I don't think I'd be able to carry
Okay, good morning, everybody, and thank you for being here. Welcome to Purdue Lunabotics 2025-2026 Critical Design Review. Thank you for being here despite the cold, blistering weather outside. And if you are joining over the live stream, thank you for being here as well and willing to support our team. We have a lot to get through, so I'll be brief. We'll start with attendance. Students who are here in person and are currently on the team, please fill out the attendance form so we know that you are here. If you are joining live, or if you are no longer on the team, or you are a faculty member, industry partner, or sponsor, no need to fill this out. This is for our own personal references. Okay. Without further ado, I'll hand it over to our Vice President, Lily, to go over the agenda for today. Lily?
Okay, starting the agenda, and sorry if I don't quite have like a full voice. Fun times. So, kind of standard agenda. We're going to start with systems, quick overview, and then an update for our treasurers. First half is going to be main robot, so that will go by sub-teams like usual, break in the middle, and then mini-bot will follow similar structure except for no excavation for mini-bot. There will be questions after each sub-team, and then there will be concluding remarks at the end. Okay, questions. Questions will be a little similar to how we did them at the last review gate if you were here. Guidelines, you're going to ask questions at the end of each sub-team's part. There is a designated Q&A for each sub-team. There are slide numbers at the top. If you can see them up there, they're kind of small, but they are there. If you need to refer to a slide, it is nice to have that, especially with the diagram on that slide. If you have questions about the main bot, please ask them during the main bot section. If you have questions about the mini bot, please ask them during the mini bot section. There's a reason we have two separate sections. Keep those sections separate if we can. Don't ask questions that haven't already been asked. We're going to try to keep a list of the questions that you can see, hopefully, so you'll be able to see if something has been answered. We also do have meeting notes that are available in Google Drive. If you want to pull those up at any time and see what has been answered, they will be in there as well. And then Slido, similar to last time, we are going to use Slido. However, it's going to be implemented a little bit differently. Please, first thing, make sure you have your name in the name box. The big thing we're going to do with Slido is so we can keep track of questions. And if we run out of time, we can follow up with you afterwards about those questions. However, if you do not put your name, we cannot follow up with you because we do not know who Anonymous is. So put your name in that box or you will not get your question answered. Questions will be answered verbally, so raise your hand. It would be great if you can type that into Slido too, just so we can have a reference of who it is and what the question is, and then we can write it down a little bit easier. We do only have 100 participants per Slido, so if you're sitting with a group, try to make sure you can like share that access. You can also just put your name at the end of the question if you want that as well. Why are we using Slido? You might wonder. That's a lot of things to figure out, to keep in mind. It tracks what's been asked and been answered, and it's a lot easier for us trying to do documentation so we have a record of what actually happens during CDR. It's a lot to type out all the questions and all the answers, especially when they're like going pretty fast. So when we have that record, or like at least a foundation for the record in Slido, it makes it a little easier for us. It can also be used for both in-person questions and online questions. And plus, like I mentioned before, if we run out of time for a sub-team, we can have those questions for later. This is going to be the option to join Slido. You can use that QR code. You can also go to Slido and use the code CDR. It's really complicated this time, 3 whole letters. I believe that is going to be, I'm going to leave that up for a second. If you ever want to open it at any point, just remember the code is CDR. That's all you need to know. Just go to Slido. Cool. Systems.
Okay, so starting with the concept of operations, real quick, the reason why we're even doing 2 robots is because one can deposit and one can excavate at the same time. So this flowchart is just a high-level overview to bring what software is designed for how the robots think to everyone else so they can understand what's actually going on in the robot, as well as for anyone else, specifically NASA, looking at how we built the robot.
Okay, so to go over the flowchart a little bit, what's going to happen is the mini-bot will first publish the meetup location. The main bot will then meet the mini-bot at the meeting location before going to excavate. After excavating, the main bot will then meet up with the mini-bot, and then the main bot will continue to excavate as the mini-bot deposits the red goods into the deposition zone.
And this will loop until the end of the time.
Okay. Next, Systems has an integration plan and risk assessment. This was developed a few years ago, but we continue to use and update it every year. This is a great way for us to map out what we identify as our highest priority risks and lowest priority risks. Some of these are more operational focused instead of being very specific to maybe like what a DFMEA does with identifying risks on a certain subsystem. To go over the highest risks we've identified, shifts in the project focus. Obviously this year with the mini robot, there's a lot of extra work that needs to get done and a lot of extra work specifically on integration of the 2 robots. So we identified this as a high risk with the addition of new sub-projects and trying to stick on the same timeline as we usually would have with only 1 robot, but now we have 2. Next, forgetting and missing deadlines. This kind of comes with the addition of Minibot as well and that shift in project focus. We want to make sure we're still hitting all of those same deadlines with 2 robots instead of 1. For example, we decided to place CDR on the 2nd January back for the semester instead of the 1st, which we were also considering because we want to make sure we have our designs pretty much done for the both of those so we can change less things hopefully by the end of after CDR, change less things. So hopefully ideas and designs don't change too much after this because of that extra week. Next, we have our RSRs, Robot System Requirements. These are the objectives that NASA set out for us and we were able to extract and put into this Excel sheet. We also put in our own input and our own judgment on designating them as mandatory, non-mandatory based on what the guidebook says. This is a way for us to organize our thoughts and what NASA wants from us so we make sure we don't miss anything. I believe a lot of people have seen these and have been looking through them because you need them to fill out the DFXs that people have done with if the certain part meets the system requirements. These objectives also help guide our TPMs, our technical performance measures. This is a way for us to then take those objectives and make it into a table that we then fill out and we fill out with our thresholds, our objectives for different measures, and then the hard limits we have for those. For example, this is the one for the main bot right now. The total limit, as you guys, most people know, is 80 kilograms. For the main bot, we're hoping to get it around 50 kilograms so we can leave 30 for the mini bot. This is a way for us to make sure that we are hitting those measures and we're not exceeding them at any point in time. We update them at most major review points. For example, there's some at PDR. We're going to have some finalized by the end of CDR for those measures. This is also really important because NASA likes to see how the robot evolved over time in terms of these objectives and technical measures. This is the TPMs for the mini bot. It's mostly the same. There's a few changes. For example, the dimensions that the robot should be in and the mass. So I'll turn it over.
So currently we are at CDR, and looking forward, we have the test readiness review. That will be where all of the assembly and all of that should be kind of finished up so we can hand things off to software to do testing and kind of get that proof of life demonstration out there, which comes after TRR. So this is something that we will be sending to NASA, a video of our robot. And then after that, we have competition. And then, so a little bit more, we also have the systems engineering paper. That's what we will be working on, and the presentation and demonstration work, and also like the editing videos for the proof of life, and TRR review slides, and other such things. And what you guys should be expecting from us is occasional check-ins to ask, kind of making sure everybody's on the same page with integration, and also monitoring the system requirements to make sure that we're on track for a good robot for competition.
Okay, and with that, does anybody have questions for systems? Alex?
And if the sum of TPMs listed a maximum robot length of 1.15 and a desired robot weight of 50 kilograms, are those still accurate?
Those were designed and designated at the beginning of that process for the main mini bot. Those thresholds are what we're hoping they are going to be. Those are going to stay the same, but they aren't always going to be accurate. We'll add a new column maybe after CDR to get that kind of estimate of what it is going to be at. And that was just at the beginning of the design process what we were aiming for. Anyone else? Okay, and then with that, I'll hand it over to the treasurer.
So we are currently projected to be spending $41,000 on the robot as well as all other costs for the club this year. This is an increase from previous years, partly due to the UK trip, the mini bot, and just generally increasing costs. This is how much we've spent so far, primarily on the UK trip and some of the other parts that we've gotten, as well as the test bit. Other updates on the treasurer's end, we've gotten a few new sponsors. We got a Regulate discount from the soil makers. We've gotten a Send Good Send has given us credits towards purchasing items from them, and NASA has provided us with UK trip support, which has all greatly improved our budget and being able to pay for all of these costs. Other reminders, make sure to work with your sub-team leads to find appropriate vendors for all of your parts. Make sure to get approval from either the treasurer or the president for orders above $100, and make sure to submit your reimbursement requests 3 months after you have received your product. So in general, you're supposed to wait to file these reimbursements until after you got it so that you don't have to deal with getting money back from or returning money to the club. That's it.
And now we're going to begin with the high-level robot overview for our main robot. Overall system is comprised of both a main and a mini robot. We will cover a lot of the mini dimensions and mass later. So our current overall system dimensions are 1.459 meters in length, 0.749 meters in width, and 0.732 meters in height. So far, this fits within the volumetric constraints set by NASA. The mini bot is included in these dimensions. The main bot dimensions specifically are 1.156 meters in length, 0.749 meters in width, and 0.732 meters in height. Overall system mass right now is around 76.57 kilograms. Our mass is 80 kilograms, and we do not have electrical components within our electrical boxes yet. So we do need to go through some major weight saving efforts before we can officially finalize a lot of our design. And then right now, the main bot mass is sitting at 47.72 kilograms. We have 3 system configurations while the robot is going to be running during arena. This is a starting configuration, so we fit within the stowed, our maximum allowed stowed dimensions. Next is our mining configuration, where excavation extends downward so we can collect the regolith. And then our third is our traversal, where the excavation system is raised up to provide additional ground clearance. And then the mini-bot deposition flap, which we hear more about later, will open up. Now I'm going to invite Will Dansdown, who has done a lot of calculations to justify the mini-bot in addition to our main bot. So we're going to talk through that.
Hey everybody. So in an attempt to justify this 2-robot idea, I took it upon myself to try to model last year's robots based upon this year's format. So what we did is I took the sample size of all the teams that qualified to KSC, or the top 10 teams at competition last year. I rewatched all of their quote unquote best runs, which I determined by taking their total volume deposited divided by the time of the run. So if their KSC run was over 2 times the volume of one of their UFC runs, I would use their KSC run. And then when I was watching those runs, I noted their traversal time, excavation time, deposit time, and how many X-depth cycles were done in totality. And one thing to note is for certain teams, I wanted a greater sample size of things like their traversal time. So I would rewatch, and on average, for something like the traversal time, I watched 3 of their 4 runs to get an accurate estimate of how long it took them to traverse. I then used the UCF given data sheet that you can see, which has a lot of things such as robot mass, energy consumption, and use that to calculate points to for the score predictor. And once I had all this data, I put it all into a MATLAB script, which modeled the behavior of robots this year, such as excavating, traverse, deposits, traverse, excavate, traverse, deposit, etc. But how does this pertain to this year's robot? So to correlate the results to this year's format and this year's robot, I created 2 different models to show how this 2-robot design integrates with the competition. And this first one we'll be looking at is what I call the pessimistic route, in which we have we assume that there's 50% losses of volume, so we have 15 liters of volume per cycle. We have the highest energy consumption at competition last year of 116 kilowatt hours, which is notably around 3 times the average, and the highest allowable mass of 80 kilograms. From that, the total volume that we mined during that time comes out to a point value of 245, and our total score being 856. And you can see the other score values taken there. For the calculation of our score value and our behavior, the times that I decided to use we used the same traversal time that we had last year of 88 seconds. And we used a slightly higher time for deposition into the mini robot and deposition into the deposition zone due to our higher volume being carried. Our next model is what I'm calling the optimistic model, in which there's only 25% losses of total volume throughout the run. So per cycle, this would come out to 22.5 liters. Our energy consumption is double the average energy consumption of robots at runs, since we're using 2 robots, and a mass of 75 kilograms. From that, our volume score jumps to 404 points. So some conclusions we can draw from this is that looking at last year's robot and how it compares to this 2-robot idea, last year's robot only scores 110 points from the total volume score. You can see that it still does well in the competition. However, even if we take the pessimistic view of the robots in this environment, we're still scoring around 100 points extra in comparison to last year's robot. which I think brings validation to the two-robot design. You can also see the other score values per team listed there. Questions?
Thinking about pessimistic, is there any chance where, did you look at what would happen if, like, you are just unable to communicate between the two robots during a run?
Yes, so one thing that I did assume is that every robot has a successful run. So I did not put in calculations anything of the two robots failing, us being stuck in ditches, a robot failing entirely. I did not put that in consideration. All robots, including the two robot design, is assumed to be working. The pessimistic view is just a lower level of working.
So, what, like, because we've done the score analysis, if the mini bot got stuck in a ditch, do you think that the score would end up looking similar to the 2024-2025 score for us?
That's a good question. I'm not exactly sure. I think it would look somewhat similar. However, our score would definitely drop because our traversal time and our deposition time may look somewhat similar. I think our excavation time may be somewhat faster than last year. However, we would have a much higher mass, which our points are being divided by, which would affect our score quite significantly. Any other questions? Hans?
I just want to say I think you did a really good job with this. This is some really nice work.
Thank you. Yes.
Excuse me, if the mini bot ends up failing, is there a fail-safe in place where we still be able to deposit material from the new robot?
Yeah, so if the main robot, or the mini robot were to fail, I believe the working idea would be that we would go on with one robot, with the main robot, and use behavior similar to what we did last year, which is just ditch the mini robot on the field and continue with the robot one robot for the competition run. Sophia?
This is more of like a comment than anything, but you see it's like a super small place that we're working with compared to KFC. So my only concern would be like having two robots in such a tight space, like how they'll maneuver against each other, especially if there's an obstacle in the middle of them too. So I think that's definitely something, obviously, like, I think software's been thinking about that, because it's really tight. Like, it worked really well when we had one robot, and when we have the mini bot, it's like going back and forth. But
I will say for notably, you can see that there's certain scores that are spiking in these graphs. This is because traversal times are pretty low, especially in last year's format. However, because the UCF has a smaller field and therefore smaller traversal, the scores will be more leveled out as teams will have a more level playing field in total traversal time. But yes. Anything else? Okay, we're moving on to excavation. Okay, I'm Will Dance. I'm the excavation lead as well. I know I was just here, but this is what we've been working on. So for our overview, we are using a bucket elevator system similar to previous years with a focus on reliability and compatibility with deposition and drivetrain. We are using the same motor as last year, which is a 200-watt motor with a 20-to-1 gearbox reduction. We have an estimated volume throughput of 20 liters per minute, which is actually calculated with a 50% loss in mind. So if you take the loss out of this, we are actually running at a 40 liters per minute estimated volume throughput. And our mass estimate currently is just under 20 kilos at 19.59, and our dimensions are as seen. There's been many comments that we look very similar to last year's robot. However, there have been a lot of things that have changed, such as we have a completely different bucket design. Our belt width has increased significantly with an increased belt length. We have a complete new drum design. We have a lot of structural rod changes. We have implemented faster linear actuators. We have created a new linear actuator mounts. We've changed our chain tensioner design, and we have updated to a modular Dutch shroud.
So for the new bucket designs, compared to PDR, we decided that it would probably be better to have a smaller footprint, and volume throughput is not as important as initially thought. So we decided to downsize the buckets and therefore downsize volume throughput. We also slightly increased the amount of buckets from PDR to somewhat compensate the volume throughput losses. The buckets are now still the same size as last year, same cross-sectional size, so 1-inch L channels, which is easy to source, and they're wider than last year. Again, as Will said, we're estimating about 50% losses, so that's where our 20 liters per minute estimation comes from. Yeah.
So here you can see the internal dimensions of the bucket. Comes out to just over 0.1 liters for our overall internal volume. The way these are built is with the thicker L channel in the back and then a thinner piece of sheet metal. And you can see here, if you look closely, those pieces are overlapping slightly to help with making our welding easier and stronger. All this comes out to about 0.1 kilograms of weight. So totaled over 18 buckets, that's about 2.04 kilograms and 1.89 liters of total volume.
In our drums this year, we are using a split drum assembly where we have two 3D printed drums on the sides and an aluminum drum in the middle. And then we have 3D printed spacers spacers in between for weight savings. And then on the edges of the drum, we have aluminum plates to stop the dust from escaping on the sides.
So anyone that was here in our previous design reviews will notice that there have been some changes. The most visibly jarring one is those spacers are now much smaller. It's kind of difficult to see from this image, but imagine it almost as a very oddly proportioned yo-yo. That tiny thing you see in the middle is very small to save on the weight saving. Then on the sides, it fans out and it has the big sides to maintain full contact with the drums in order to fully keep them in place. From our suggestions from the last design review, we did switch the 3D printed in aluminum drums because most of the weight is going to be concentrated on the center one. We need that aluminum with the sides 3D printed, and that also helps with weight saving. And then the last main change was for each drum, you see that side view, we changed it to have 6 spokes instead of 5. This just helps with the increased integrity. And because we had more spokes, we were able to shape them down a bit, so there wasn't too much of an increase on the weight saving, on the weight for those.
So there's a lot of concerns about this drum rod during PDR, so it's changed like quite a bit. We swapped it out. It used to be like a 1/2-inch cylindrical like steel rod. Previously, we've had a 1/2-inch aluminum rod through this part on robots of past years, and it's actually experienced a failure mode that looks like a banana almost, where it'll start to flex inwards and upwards. So we chose to upsize this and then also make it into a hex rod that also enables us not to have to key every single drum component in the center. We also are going to lathe the ends of this 3/4-inch hex rod to be 3/4-inch cylinders, only on the end pieces just because it's super hard and impossible to source bearings, sprockets, and shaft colors for a 3/4-inch hex rod. We've looked into weight saving for this part because obviously it's super heavy since it's 100% steel. We've looked into carbon fiber hex tubes, and then we'll use some sort of metal insert on the ends to make it a cylinder that would almost like slot into this carbon fiber hex tube. The factor of safety is about half of what it is for if we just kept it solid steel. I think this part of the robot's also going through a lot of stress and direct forces. So I don't believe cutting weight on this rod would be smart. But I do feel more comfortable with this design compared to PDR. And then this was also gone over in PDR, but we're making our struck rods solid carbon fiber rods instead of steel. That should save a lot of weight.
Also, the forces this is experience is a lot better for our carbon fiber application than if we were to make the drum rod carbon fiber. And all the calculations for this you can see in the PDR slides, but I included a table that we had up there last design review.
For the chain tensioner, we'll be using a small aluminum block directly bolted onto the side plate before assembly, and it'll have 2 through holes for 2 screws. And on the end of the screws, we'll have a rod that has 2 threaded holes. The rod will hold we'll be using a 22 tooth number 25 bearing sprocket, and to tension, we'll just turn the screws at the same time, pulling the chain and tensioning it.
Our chain tensioner is gonna have a dust shroud or dust cover that's gonna be 3D printed, made from 3D printed PLA. It's gonna be mounted using flaps that go in between the dust shroud and the chain tensioner plate to keep the dust from entering the chain tensioner, and it's gonna be attached to the top plate using screws. We're also gonna seal the edges with aluminum tape.
So for our linear actuator, we decided to change how we would mount it because previously it would go through a pivot almost, and it would be able to rotate as a result. We didn't want to do that, so we decided to create a part that would go over this pivot that would hold it in place and prevent it from rotating, as you can see here, by holding the pivot inside of the cutout and screwing 3 screws through the piece into the linear actuator itself. This helps keep the linear actuator more stable and prevents that rotation.
I'll introduce some key parameters of our new linear actuator. It uses feedback IP65 linear actuator and have 24 VDC for voltage compatibility and 8-inch of stroke length, and can provide 56 pounds of static and dynamic force and have an approximate weight of 0.98 kilogram. And the pancake tensioner is the part providing the tension to the belts that prevents the belt from being too loose or dropping off by putting the 2 plates together.
So the plate is tensioned by loosening the clamps and then either tightening or loosening the nuts and the screws. And using these lead screws, we can either push the plates farther apart or pull them closer together, which will change the length in between the drums and therefore help tension the belt. And it uses 2 lead screws, which are now farther apart to create more space for the new, larger structural rod clamps that we have. Thank you.
So we're implementing a dust shroud similar to last year's, but we have some significant changes. First of all, you can see it's very modular compared to last year's, but the intent remains the same. We're just trying to cover that rotating belt system and deposition area to contain as much dust as possible that results from excavating. The coverage will be similar to last year. We're going to rivet nylon into the structure, and this is going to be mounted onto the excavation system.
So some main improvements that we're adding this year are the 2-piece design, like she mentioned. This means that the portion covering the buckets is removable using these buckles. Also, this design means that we don't have to mount the dust cover through the same holes as the linear actuators, which was a big problem last year because they had to take the whole thing apart to take the dust cover off. In addition, there's additional coverage over several areas, including the excavation deposition meeting point that prevents dust from spewing, and over the sides. Those side panels also have cutouts in them for weight saving. And finally, we're planning to make this using laser cut polycarbonate and some 3D printed parts to save weight.
As mentioned before, we will be connecting the 2 parts using a buckle. It will be 3D printed using PLA or PLA+. The way it works is simply as a lock, where if you put the 2 pieces together, they will simply
lock, and you need to push down on the tab to make the release. This should be easy and fast with 2 to 3 people, and it will allow us to, as mentioned before, get into the bucket system and make any changes we have to quickly without having to unscrew a whole system.
Okay, so this year we are planning to create a bucket testing rig so we can test some mining forces roughly on the buckets. So how it's generally going to work is we're going to have linear bearings, and we're going to attach encoders onto the winch that we use to pull the buckets as they are in regolith in our test bed, or in our test pit. And then using the encoder, we're going to calculate position data and use that to calculate force and velocity and find relations that we can use to estimate mining forces in the future. Other general informations, we are using a wooden frame that we're going to place in the test pit, and we're going to use the drivetrain motor for power.
To find the drag forces entirely, we are aiming to find a correlation between the flow velocity and the drag coefficient, which we will then use to find the drag force and apply to the rest of the robot. This correlation is going to be used to find the mining forces, which we will then be able to use to find weight savings across the entire robot. The plot you see before you is a simulated example of what a test might look like. This is not representative of an actual test we have done.
In terms of the DFMEA, a lot of it is pretty similar to the last design review. A few more concerns that we have is over drums, which was a big concern before, and how we're changing it to be aluminum at the core and PLA at the sides. A lot of it comes down to like proper assembly and making sure we don't overexhaust the system when we're running it. Another concern that we have is chain tensioner with how we're assembling it and the rods and everything like that. So a lot of it comes down to proper assembly. And then structural rods, carbon fiber, brand new this semester or this year. So we're making sure that that's also assembled and manufactured correctly.
Okay, so after CDR, some of our priorities moving forward is discussing and implementing any feedback we get from CDR, finalizing manufacturing plans and schedule, begin manufacturing assembly, use the bucket testing rig to get the mining force calculations, and then assist in any robot testing possible. Questions? Peter.
So my first question is, if you go back to the slide showing the drums, specifically this slide right here. So the aluminum drum will have a hex cut in the middle, question mark?
Yes.
Yes? Is there any concern that the water jet might not be able to cut the corners of that sharp enough to be able to match the hex shaft? And so is there any plan to maybe add leaves into that?
I didn't think about that. I don't know if there's lots of
The water jet does not have a point cutting diameter, so the corners will be rounded. I think leaf cuts are a good idea. I think that'll also reduce the stress concentrations on the part. Yeah, we don't weaken anything dramatically by adding.
Yeah, so that's just going to be adding small holes at each of the corners that the water jet cuts out. My other question, and this was just an idea of weight shaping for the shaft, well, which I brought up last night, but for this, so I'm noticing quite a bit of stick out on one end of the hex shaft, So it's very possible that we could shorten that down, and then instead of using a lock collar, shaft collar, sorry, you could use a retaining ring to hold it in.
Yeah, I'm not opposed to that, honestly. I think that's something we would have to do after we see what the tolerance stack that it looks like on all these parts, because it's a permanent groove for the retaining collar, right? You're pushing it for
Yeah.
That's how it stays on. Yeah, like, I'm not opposed to that idea. I just think like if you were to just predict where it's gonna be, it's not gonna be that in that place.
I mean, I think there are ways we can get around that. We can try to move it a little bit off of where we think it would be and then have a spacer in between.
Yeah.
But that's just something, maybe something that has to happen afterwards, but it's something to think about, because if it does cut off, it looks like maybe half an inch or so of steel, 3/4 of an inch, that's gonna save some weight.
Yeah, especially if we still have weight concerns following CDR, we can definitely look more into that as well.
Yeah, speaking of weight concerns, the linear actuator mount. Yes, that one right there. So that looks like a fairly beefy piece. Is planned to make this out of aluminum or 3D printed?
The plan was to make this out of aluminum, yes.
Why?
Just for structure.
So there isn't that much force that's actually trying to twist the linear actuator, right?
I do not believe so.
Should be. And even if there is, the pivot point is right there, so there shouldn't be too much lateral force being experienced, even if this being experiencing a torsion torque, right?
I believe that is true.
So I suspect that this piece could probably be reduced in weight, either with like weight saving holes or making it thinner, or 3D printing it.
Okay.
And if people disagree with that, then I feel like this could probably be reduced in weight. And then also, while we're here, do you have the numbers for the speed of the linear actuator?
No, but it's about, I believe, 1.3 meters per second.
Okay, and how does that compare to last year's?
I believe the last year's was about half.
Okay, excellent. For the structural rods, yes. No, the part we're talking about, the pancake tension, sorry, what I actually.
Yes.
Yes. So you mentioned making space for the new larger structural rod clamps. Why are the structural rod clamps larger than last year?
This is because last year's structural rod clamps, we custom manufactured them and they were unable to actually clamp on the rod. The screw we had that went in the block turned out it had it was not clamping whatsoever. And so we've decided to go back to bought clamps.
Okay.
No, on that. If last year's weren't clamping, then what is it? And the robot, to my knowledge, still worked just fine last year. What is the point of having them at all?
It's just to add an extra fail-safe in the event something was going wrong, because you also want them because the pancake tensioner is being held by the two lead screw nuts. However, if you have the clamps as well, it adds an extra layer of fail-safe to the pancake tensioner, and it would reduce the amount that the pancake tensioner becomes untensioned over time. Yeah.
And while we're here, I'm noticing the bolts being the bolts going into the bottom of the structural rods. I'm not familiar with working with carbon fiber particularly at all. Is that going to be a problem having threads in a solid carbon fiber tube?
From what I've looked through, that should not be an issue.
Okay. And then I think the point on the structural rods on the clamps is a good one, in that if we didn't need them last year. And then I'd also maybe encourage trying to look into using look into just changing last year's clamps to clamp better. If the problem was not having a large enough gap, or if the problem was the screw wasn't strong enough, or something like that. Because in my experience, the structural rod clamps are quite big and quite expensive. And given that we're trying to look for weight savings, it's a potential avenue to save lots of grams. For the dust strap connector.
I will note, for weight reasons, last year our custom-made clamps were actually heavier than these that we have in CAD right now. Yes.
Then I don't know. I think we could probably make them lighter. Anyway, the dust strap connector. Has this mechanism been tested?
Yes.
Printed out?
We have tested out a sample version and it has worked well.
Perfect. And then for the test rate, how are you planning to calculate the force based off the velocity?
We're gonna, because the encoder has a high enough fidelity, we plan to take the second derivative using the position data given from the encoder after converting it obviously to the linear.
Okay, wait, so you take the second derivative
First
of so the second derivative, and then you're just doing, divide by mass, or the first derivative divide by mass of some kind and get force, or multiply by mass against force?
With the second derivative, we have a free body diagram on the actual bucket itself, calculating where the drag force is on that. And using that dynamics, you can
So
figure
I guess,
out the drag force.
one of my questions is why not just have a pull scale?
A what?
A pull scale, like a tension scale.
It is harder to implement from what I can see because it's harder to get a consistent pull, and also harder to, it's less consistent, basically.
But that is something we can look into.
Okay.
Alex?
This may be me not understanding your calculations, but most motors draw more power when they are under load, to prevent the dropping in RPM, to prevent dropping in speed. How will you tell in a motor that is spinning, the spinning and unloaded, let's spinning at say 100 RPM, and completely unloaded, or a motor that's spinning 100 RPM, but is drawing a ton of current and is working really hard?
We are able to calculate the force and the velocity at any given time. So we can kind of bypass that.
From what data?
The position data of the encoder, as far as I understand.
Right. My point is that if the motor simply draws more power but doesn't change its speed,
it would change its force, which means the speed would then accelerate or decelerate based on.
I'm not sure it will.
Okay, I'll look into it.
Yeah, I think that might just be us needing to look over the math of this.
Probably.
Afterwards.
Dr. Marshall?
I think Peter's right, you need to calibrate it. And so that would be a situation where you would use a tensioner, or you could put weights inside the buckets possibly, but then, I mean, I guess you could tape them in there, so, I don't know how, it would fall out of it, obviously, but, maybe you could tape them in there, and it would take different, do different tests where you do different amounts of weight, and then you can calibrate to the power draw. But what would the force tell you?
So the goal with the mining forces experiment is to both roughly see if, make it easier to model in FEA the loads on the buckets, and also easier to roughly calculate power draw, which I don't know if it's that important right now, but it will help us in calculating power draw for the future while running excavation.
Also, when are you planning on doing these tests? And will they affect this year's design, or is this a we want to have this in the future?
Yes, so we plan to implement these tests after the robot is assembled. So during the period in which the robot is assembled and excavation does not have much to do, and ordinarily we would be showing up and making sure the tensions are correct and fixing anything. Any dead time we have, then we will be working on the bucket testing and the calculations. Yes.
I have a question regarding the cheese rod. I know that you were mentioning reducing the weight with carbon fiber. What was the reason against why you didn't want to do that? Was it the manufacturing of it?
Carbon fiber for the X rod? Yeah.
Oh, yes.
Yeah, so the original idea was to make the center part, the X carbon fiber. It's the factor of safety is like half of what it would be for steel. This is experiencing, especially, we don't want to put carbon fiber in this kind of force. The struck rods are running vertically. This is running horizontally. Carbon fiber usually is not good for that kind of application. You don't want to put it under that load. So that's why we kind of steered away from it. These two weigh a decent amount because they're steel, but I do believe they weigh they're sturdy part for a reason. This is probably the point where a robot's experiencing the most stress. Is this? It's going straight into the ground, actuating down. So.
For some reference on that, I did run some calculations, and a 3/4 inch carbon fiber tube that I was able to find has about the same strength as a 1/2 inch steel rod, which we already had concerns with it bending and breaking over time. So, the fact safety is less, but we also, the data what we have that is not quite strong enough and it'd be weaker than that data.
Yeah, I think the failure mode especially when the steel was bananing, I can't even imagine in a carbon fiber where they start cracking. It's a lot more of an extreme mode of failure to put that.
Hans?
I have some questions from Julian from the slide out.
Yes.
First of all, how are you getting the motor in? It doesn't look like there's any holes inside.
Yes, so the motor, I believe we will attach and put that onto the plate prior to assembling the two plates together. So that will be, we will be putting the motor onto the plate prior to assembling the top drum assembly.
Okay. Another question. It looks like the linear actuator mount is mounted to the plate via threaded holes and might require a redesign if you choose to 3D print that.
Yes. So the screws actually. So the entire reason why you see the 3 screws in the linear actuator mount is because we're doing something very interesting this year, which is there are 3 screws on the bottom of the linear actuator. Our plan to increase the points of contact with the linear actuator is to unscrew the screws in the linear actuator and then add longer screws that go through the bottom plate, the L channel, into the linear actuator mount block and then into the linear actuator to increase the amount of points of contact we have with the linear actuator.
Another concern from Julian, the pancake tensioner bolts moved to the outside this year. Moving the location of the load outside the pancake plate might make it bend.
Yes, this is a concern. However, I ran some FEA on it 2 days ago, and I do not think this will be a problem.
Okay. And it looks like Julian has some pretty serious concerns regarding the carbon fiber strut rods, specifically in compression and tapping them. He believes that it would be difficult to tap the rods without deforming them or causing other defects.
Yeah, I do believe when I did this carbon fiber rod calculations, I can also send them to Julia, and we did not consider threading them. So definitely adding any sort of feature that was not there when the carbon fiber was manufactured is going to cause stress points and issues. So I think it's very valid.
Okay. I would like to note that we are getting these carbon fibers rides at either a very heavy discount or for free.
Yes.
So if this doesn't pan out, it's at no financial risk to the team, which is good since carbon fiber is normally very expensive.
This is true. One failsafe we had at PDR was initially we were trying to use carbon fiber tubes. And so we had the truck rod clamps that we were looking at earlier. We had those between the pancake, it's easier if I go to this, where the area between those 2 plates, we are able to implement clamps there in place of screwing into the rods, which is something we've already thought about. And if screwing into the rods itself is too much of a concern, we can always go back to that idea. Alex.
I have some questions about Julian actuator mounting. So first, your plan is to unscrew the bolts that are holding on that bottom cap and screw them into there.
Yes.
Are you concerned that those bolts are not at all rated or designed to support any load, and you're using them for something that are not designed to be used for?
Yes, so this is something we've thought about, and this will kind of be a wait and see once we actually receive linear actuators, how possible this is. It may very well be that this is something we should very much not be doing, and if that is the case, we'll be going to just the 1 point of application through the designated amounts.
Also, how is the whole linear actuator assembly attached to the frame itself? I don't think those 3 little bolts are strong.
There's 3 bolts going through, and then if you also see on the side plate that is also connected to drivetrain, there is a tab that comes up that we also screw through that goes through the linear actuator mounting hole as well.
Is that attached on one side or both sides?
It goes through the linear actuator block, and there's we screw it on the back, so it's not attached to the plates on both sides, but it is.
Are you concerned about, because right now, when the linear actuator is being pulled up with that plate, you're relying on the bending strength of that bolt.
This is what we had done last year and every other year.
Okay.
The added holes is just to add extra strength. However, we have had no direct issues with the linear actuator mounting with the 1 screw in the past.
I mean specifically is that, to my knowledge, I could be misremembering, that last year's had a U shape with the linear actuator sitting in the middle and being attached on both sides. This year, that's no longer the case, and you're just attaching the linear actuator on one side.
This is true. However, I do believe that because the linear actuator mount is sitting within the block, if we cannot screw into the linear actuator itself, we will still screw the linear actuator block into the plate, and that will act as the U.
You're worried about the fasteners like failing before the actual mount?
So I'm worried about the three small screws.
Yeah.
Is there anything about the size of the screws we've taken out, like when we used to attach the dust rod on the motors?
Yeah.
Those are going to be very strong, very weak. They should not be able to resist the forces, and that's not what they were designed to do. My other concern is that Historically, you have done like a U-shaped attachment point, and this time you're not. You're just attaching it on one side. And I'm concerned about, the linear actuator bending with weird force.
Yeah, I think that's a valid concern. Also, if the fasteners are failing though, that's a point of concern if we were to make this into a 3D printed part, because then that means there's some sort of force happening there.
For the sake of time, we'll only be taking a few more questions.
Kyle?
You've talked a lot about using carbon fiber tubes for things. Have you looked at using steel tubes?
Yeah, we actually have for the struck rods, we're just trying to save weight on that. So I do have factors of safety for, I had in my spreadsheet, I had a factor of safety for a steel tube. It's just, this is for the sake of weight saving that we've started applying carbon fiber. We have gotten into like the points where we're looking at like just putting weight saving holes and like random things to shave weight. So it's been a battle for like every gram of weight. Yeah, obviously, like I'd be more comfortable using like steel than carbon fiber, especially when stress is applied, but it's just been.
I would personally be a little concerned about using carbon fiber tubes in compression here, because carbon fiber kind of sucks in compression.
Yeah, this isn't, they're solid, they're not tubes for the struck rods, but yeah, I agree. We did factors of safety for both compression and then buckling, so.
Like, I'm kind of surprised that the carbon fiber tubes are passing their test, because their strength in compression is like less than half of their strength in tension. Like, I think that they're like maybe like fish.
Yeah, I can share with you the Excel. Yeah, yeah, these aren't. The factor of safety was actually fine too when it was like a tube with like 1/8 of an inch like wall thickness, but these are solid for now. So, yeah, I agree with your concerns. So, I think
these are concerns we've been thinking about since we begun thinking about using carbon fiber. The calculations show that we should not have issues. However, Sophia can send you the calculations to ensure that.
For the sake of time, we'll be moving on to deposition now. Any questions you may still have can be dropped into the Slido. And excavation, if you guys can go through and answer the unanswered questions that were not raised during this discussion after this now, that would be great.
Yes.
Thank you, excavation.
Okay. Well, this is deposition. Go ahead. Take it away.
So this is kind of a look at our system. The overall dimensions are around 24 by 16 by 10 inches, which can hold around 30.6 liters when fully filled. When the system's mounted on the main bot, the belt's going to be tilted at about a 20-degree angle, which will take 2 seconds to deposit when full. And the overall weight of the system we found to be around 6.9 kilograms.
All right, for the belt, while the overall conveyor idea has stayed consistent between last year and this year, a change we've made is going from a nylon belt to a fabric belt. The main reason behind this is the weight saving we got out of this, about 2.5 kilograms we've calculated. For the other parts of the design, all things stay consistent, like the tensioner pin and block as you see in the top or the right image, as well as nesting the motor now into the system itself, seen in the bottom left image.
So at the back of our system, we have a gate which allows us to pile up regolith against the back of the system and then open it up. A change we've made from PDR is instead of having the gate being opened and closed actively, the gate is now open and closes passively simply by regolith pushing the gate open as the belt turns. And so instead we have servo motors which move in latches that hold the gate closed instead of having servos actuate the gate to keep it open and closed. This simplifies the design significantly and hopefully will also make it stronger and more resistant to regolith. The latches themselves have a slope design implemented such that if the gate doesn't naturally close all the way, then the latches should be able to pull it closed slightly through their rotation motion. And in this way, direct motor power is not necessary to hold the gate closed, as mentioned. For dust mitigation this year, keeping the main focus of this is keeping the dust from getting into the sides of the belt. So we are going to be buying some 1/16 inch rubber strips, which we are going to be bolting onto the sides of the robot. As you can see in these images, the plan is for these to be bolted slightly below where sort of the length of them would have them sitting on the belt, such that they will actually be bending on the bottom of the belt in order to create a nice seal with the belt. This bending has some advantages. This is an idea taken from our observations of industry conveyor belt sightings. But one of the advantages is that because the rubber is deforming, it is bending around the belt. If the belt sags at all through the regolith weight, then the seal should be able to match that sagging somewhat and still maintain a seal. And these are just going to use the same mounting holes as the sidewalls for deposition will be mounting with.
Here we have our updated design failure mode and effects analysis. The main takeaway from this analysis was that most of the possible issues with our system deal with really dust mitigation and regolith getting to places where it's not supposed to be, which is why we've taken a lot of time in focusing on first the dust covers, as well as now the rubber flaps.
So some of our priorities moving forward would be to implement any feedback we get here at CDR, further testing the belt material to see if it fits our requirements, preparing for manufacturing such as cam drawings and other things like that, ordering materials, and then final assembly.
Are there any questions? Alex?
From your dust sealing, you got a little rubber beds.
Yep.
Are you concerned about extra friction that is added to the belt?
Not particularly. So potentially, but the rubber is only a 1/16 of an inch. So, right, yeah, the rubber is only a 1/16 of an inch thick. So we don't expect it to be generating a large amount of friction. And even if it is, the belt is not the most sticky thing in the world. So hopefully it should be fine. And if it is, then last year, from last year's testing, the motor was not drawing particularly much power to actually turn it. So even if there is a little bit more friction, I don't think it'll cause any sort of a larger problem such as a motor stall. Yes.
And on your chain, how are you planning on tensioning that?
So the chain is planned to not have an external tensioner. We've just spaced them very carefully such that there is just slightly less distance than would perfectly take up the links. This shouldn't be a problem. The worst case scenario is that if there is tension, given how much wrap angle there is, even if there is some amount of sag in the chain, that just means that worst case scenario, there is a slight delay between starting up deposition and it turning. And we don't foresee this to be a large problem.
Are you concerned about being too tight and being unable to put the belt on?
We can double check, but right now that hopefully should not be a problem. Okay, yes.
Going to the gate, how much force is it going to take to open this gate, and have we tested it? Or are we concerned about
So we have tested the gate, not obviously in its sort of full design, but just as much as we could do based on last year's system. And it seemed like the regolith had no problem pushing open the gate, even when we tilted it as much as 30 degrees. Yes, Dr. Marshall.
Is that going to affect how much you can fill the deposition during excavation?
Hopefully not. This is the same. This is the same basic plan that we've had the whole time, in that the gate will be sort of held closed, and the regolith will still be able to pile up against the end of it. So it's just that we have the latches holding the gate closed, and we piled the regolith, and then we just open the latches, and now the belt can push the regolith. The regolith can push the gate open. Sophia, do you have a question?
Yeah, I guess it was just having concerns where we just happen to we're driving over a rock now, where I see for an angle on the right, once starts piling on the gate, if the servos would be implemented with force have you considered putting like two like lines instead of those, like some holding the upper versus just like two lines on the lower half of the gate? Or I don't know if that's more points, because circles are kind of like flimsy, are you worried about like regolith getting into them because they don't look covered right now?
I don't know that we're worried about regolith getting into them. But that's not something we thought about, but it's something to be considered.
Putting two is definitely off. There's not enough space for us to put more.
Super heavy,
Mhm.
like, components and like, if, you know, if you can help out, like if you had a pair on the upper half of that.
We can definitely do it.
We can look into it. Hans.
Once the gate is open for the first time, won't gravity passively hold it open since the entire system is at an angle?
The system is angled like this. The gate is here. So if the gate gets pushed over to this, gravity is going to want to close the gate.
I see, you're right.
Will.
Are there any concerns with the regolith that excavation is pouring into deposition, piling into almost a pyramid in which the top edges of deposition will be unable to be filled?
Yes.
I think.
I was just wondering if it's just gonna start like cutting off regolith immediately now, because like you said, it's at an angle like this, and if regolith doesn't, if there's not enough regolith.
I mean, based on testing, very little regolith is required to push this open.
Also, if it pyramids up, I feel like that would be more to the advantage of this because it would be like, I don't know, it's like a cone upwards that it's not going to spill out.
Yeah.
My only concern is that last year we had a lot of problems with how we were pulling things in deposition. However, one of the problems was that we were, all the regolith was kind of coming into a pile, pyramid shapes, and that directly affected how much regolith we could hold per cycle, which greatly affects our pulling down.
Yeah. So there's a couple of things which are directly combating the problem you're describing there. One of which is the gate, right? One of the key problems with the pileup from last year is that once it piled so high, it inevitably would start falling out the end, right? But with the gate, that means that now we can just sort of raise that whole pile up vertically, right? Additionally, based on excavation interference last year, we almost didn't have the front plate here. There's almost nothing towards the bottom of that. So that also raises up and lets us get in more material. That being said, based on the angle, we do think that 30 liters is going to be probably a pretty generous estimate of the volume. Yashas?
Going off the angle thing again, have you considered agitating the regolith to reduce it?
Potentially. I'm not sure how much that might help. That's something that would have to be determined probably in testing. Will, another question?
Whenever I think of the conveyor belt moving with the deposition at an angle, I foresee it becoming an issue that instead of it piling also at an angle, it ends up piling in a triangle fashion where it levels off at the top of the conveyor belt. That you understand what I'm trying to say. Is there anything that would cause the material to actually come up to fill that gap?
No. I can actually answer this. We did do a fair amount of testing with our old robot with Reggie. So the belt angle 20 degrees, we tested up to at least 45 degrees on Reggie, and the belt did not, the regular stuff, the belt just the same and stayed in the same shape. So not
The same performance with this like cotton fabric.
So, I mean, I guess with the cotton fabric, that's one of the things that we need to test about this. There are ideas on how we might be able to apply various coatings and sealings to increase its friction if we find the regolith is sticking to it. Although I don't suspect that to be a large problem. In terms of, I think what you're saying is that basically in short, yeah.
I don't see how it would pile up vertically any higher than which the conveyor belt is because of that.
So, I mean, the answer for that is just going to have to be sort of
the motion of it being pressed up against the gate inherently sort of pushing in more underneath it, which then lifts more stuff up, and more regolith comes in underneath, which lifts it up, and then it falls backwards and fills the shape. That's something that, that's another thing that really just needs to be tested. I don't think we can know sort of how the regolith will behave in that manner.
There's also the idea of running the belt just like a little bit slowly to just distribute it a little higher.
Hans?
Yeah, question from the slide out from Julian.
Mhm.
Did the deposition gate use a solenoid instead of servos?
A solenoid instead of servos. Potentially, I don't necessarily see. I can't think right now of where the solenoid will be placed, or necessarily what the benefit of that might be as compared to the servos. So where's the solenoid? We can look into that. We can look into that after CDR. I'm having a hard time understanding where the solenoid might be in this moment.
I imagine it's like a latch or something.
Oh, like you just think like it just extends, pushes out.
That's like a space thing too.
We could maybe.
Yeah.
The good thing about the servos is that they're quite compact, right? We might have to sort of expand the bars more out to the side in order to fit the servos, or make some other sort of, or fit the solenoids, or make some other sort of mounting.
I imagine the driving requirement might be mass.
Mm-hmm.
I'm not sure which would be that.
Yeah. Unker.
For the gate, is there anything to prevent the regolith from slipping underneath the gate and sit out the back of the rope?
I've thought about potentially trying to take more of that sort of rubber siding and sort of slap it on the bottom, so sort of try to make a seal, or just having sort of a tight clearance. Either of those. Even if it does, we suspect that the amount that goes underneath it would be quite small. Are there any other questions about the system? Anything from the Slido?
Yeah, another one from Julian, more just a comment, but it might be a good idea to look into any sort of anti-slip or spray coatings for the belt.
Yeah.
Interesting how that interplay with regolith.
Mm-hmm.
Another question from an anonymous user in Slido. Would it be wise to have no power needed to hold the gate closed at all? And far-fetched, but what if the servos fail?
Would it be wise? We think that it would be wise to have no power required for the gate to. Sorry, what was the first question?
Would it be wise to have no power needed to hold the gate closed?
We think yes. We think that this current design should have no power needed to hold the gate closed. We think that is a benefit. It means that we do not have to be actively supplying power, which is of course counts against our points in the scoring. And we also think it means that we can sort of take advantage of, rather than just straight motor torque, we can try to use other mechanical tools to combat any sort of closing forces. And then far-fetched, but what if the servos fail? That is definitely a concern. And in match, in a match, it would just mean that we can no longer sort of pile up against the gate as effectively. So it would reduce our storage capacity, which would mostly impact mini, I think. I think. Yeah, if the servos fail.
I feel like it depends on like at what point it fails. Like if it's failing open, then that's that's gonna be fine.
Yeah, in terms of the servos turning, if the servos get stuck closed, I don't necessarily foresee that to be a problem. These are fairly powerful servo motors that we're using. Yes. Yashas.
How are the servos mounted? Sorry.
So it's hard to see. This might be an old, I think this might be an old image, but there are 4 M4 screws that hold them in. Sophia. Is our pulleys? I forget. I think a little bit less than a kilogram each.
They are.
Yeah, the pulleys are pretty heavy. We're going to try to look into some more potential weight saving for that by trying to reduce maybe the inner diameter. It's hard. The pulleys are very important for the system, and they're just sort of necessarily long tubes of something, and so that's sort of just a lot of volume. So we're looking into ways to try to reduce the weight cost from that. Yes.
Yeah, also on the pulley, I believe you talked about PDR, but I believe you were planning on making those pulleys, I don't know, convex or concave.
Yes, convex. So the pulleys, they are no longer to be actually properly crowned, meaning they will not have a arc on the radius. They're instead going to be sort of trapezoidal pulleys. So there will be two straight parts going into the cross section on the outside will be sort of a trapezoid, which wildly improves manufacturability of these pulleys.
You plan to manually make them?
Well, right now we're still debating between manual and CNC processes. Potentially either, depending on what's more available to us at the time.
Looking at the design, I would be fine.
Yeah.
See if you get you more accurate profile.
Yeah.
Manual will probably be a little bit faster.
We made them manually last year. I know CNC can do it, so we'll just see whatever works best for us at the time. Is there anything else for deposition? Yes.
So are you concerned about regular out from around the gate, or is that small enough that you don't care?
I don't think we're too concerned about regulars leaking out from around the side of the gate.
Great.
Yeah.
I think for the sake of time, we'll move on.
Yeah.
If you have any other questions, feel free to drop those in the Slido. If you missed it, just look up Slido. The code is CDR. We'll be moving on to drivetrain. Thank you, deposition.
Hello. Starting with the drivetrain overview, the size is within what was predicted for PDR, so is the mass. The clearance for mainbot is 3.87 inches. And then the overall changes from PDR were the wheel rim and then changing the handle design as well.
So the base frame for our system is made from 2x2 1/8-inch thick aluminum 6061 box tube, used a bunch of years in the past. The main difference that has arisen this year is using these little internal box tube connectors, which you can see towards the back to connect everything. We chose to do this because using 4 of these and all the bolts weighs less compared to our previous solutions, which were L channels and some gusset plates.
The rear gearbox has not changed that much since PDR. We have the same gear ratio, but we've included an open space to allow more easy access into the actual gearbox when assembling. And also we came up with a solution, we're not 100% sure on it yet, of using friction rings to connect the gear to the motor shaft. And John will explain how we're planning on assembling it.
So the plan for the main gearbox is to CNC mill the actual gearbox frame, and then all the spacers will be 3D printed, and then everything else will be purchased.
All right, so it's a pretty similar story with the front gearboxes. The one thing that we changed was adjusting a little bit of the alignment of the spacers to account for the chain clearance. And also another thing with the gearboxes is that I put together a step-by-step document with our plan for manufacturing and kind of just how we plan on assembling it. So that is a good thing if anyone ever interacts with the gearboxes or needs that.
So chain tensioner has changed mostly just adding the smaller parts. Not much has changed design-wise since PDR. And we got more into manufacturing. There are 6 spacers. They're all going to be 3D printed because they're not going to experience a lot of forces in any direction. And the 2 smaller sprockets on the edges, they're going to be laser cut because they're just 2D extrusions. And the main sprocket is just a standard part, but we have to cut off a bit with a soft jaw manual mill. We might have to 3D print the soft jaw, but that's what I think Andrew told me. But we might not have to, who knows? For the axle, it's just going to be lathing it into a cylinder and drilling 2 bolt holes because that's where those 2 bolts are going. For the U channel, it's just going to be a bandsaw to cut it to the right length, and then CNC or manual milling the hole and 2 slots that it's going to be attached to. For the tensioning, bare minimum, which is assuming that there's like a slight amount of slack in the chain before we tension it at all, we get 1 link, 1.08 links. And maximum, assuming that it's perfectly just not taut, like just in a straight line before we put the gear in, we get 1.5 links. Yeah.
For the wheel, some of the key dimensions are the diameter is 11 inches, the width is 5 inches, and each wheel weighs about 725 grams, 550 grams of which come from the rim, and then the hub weighs 75 grams, and the spokes weigh about 100 grams each for total. As for manufacturing, the hub will be made on ST20Y at Bechtel out of aluminum 6061, and then the rim is going to be printed out of PLA Plus on a Prusa XL, all in one part. And then we're going to look into annealing the rim with a low temperature annealing temperature of maybe like 60 degrees Celsius. And that's just due to concerns about the Florida heat and worried about the wheels heating up in the sun and then maybe somebody bumps into them or they fall and drop. We don't want the rim to break then. And we did some prototype testing. That prototype had similar characteristics to this wheel that you see on screen, but they weren't exact. But that wheel was able to withstand 180 pounds of vertical load, and the rim never failed. The hub failed, which was 3D printed.
So for this year, we decided to come up with a new way of transporting the robot in and out of the test pit and then just around competition spaces in general. So we have decided that we want to do a solid handle design. So this is kind of like a U shape. It would go across the front and the back of the robot. It has at the end like a solid piece. So the idea is that you would like slide it around the front box tube and the back box tube, and there is a strap that's kind of like a ratchet strap where you would pull the strap, tighten it, secure like a buckle, and then you would have a more secure, solid handle to pick up and carry the bot with. And it just allows you more options of like where to hold it, how to hold it, and it makes it more comfortable for everyone who has to transport the robot.
So for the DFMEA, all of the numbers look very good. The 2 highest ones were screw failure and the skid plate breaking or falling off if we're beached on a rock. For screw failure, we've kept the screw holes the same, but we've double checked them, and using 1024, there should be no issues. With the skid plate, we are keeping it at 1/8 inch thick polycarbonate instead of reducing it to save weight. In the case that we do get beached on a rock, then it will not break, and then one of the motors could get hit instead. The plan moving forward, we will be implementing CDR advice. We will be testing the wheel rim a little further, ordering stock, manufacturing parts and assembling, and working for weight saving on different pieces. Yeah.
For the handles, that bar that appears in the CAD, that counts to our mass. Anything that we bring into the Artemis Arena will count to our mass. So even like our April tags and stuff like that we brought last year, any credentials, that all counts.
Pickup mechanisms don't add.
The handles don't.
No.
So it goes on at the, like, you take it into it and then everything comes off.
Yeah.
And you take it out. It's just to get it in and out of the pit.
Yes.
It doesn't stay.
It doesn't.
Yes, it doesn't
the
stay.
whole
So
thing comes off.
Yeah.
Yeah.
Regarding the gearboxes and the sprockets inside them, what's the clearance between the chain and the rib nuts? This was a concern that we had last year, and as such, we only put 3 rib nuts in the gearboxes when we came to actually assemble. I just want to make sure that you've actually looked at the path the chain takes and make sure there's a good amount of clearance between that rib nut and chain path.
Yes, that has been checked, as well as for the skid plate and chain guard, making sure that those bolts will not hit the chain or come too close to it, which was an issue we found last year where it destroyed many master links.
Do you know what the radius of that is though?
On the chain tensioner,
Yeah. Yeah.
not off the top of my head.
It just seems really tight.
Yeah.
Like, it's like the chain right there.
The clearance in what area?
Yeah.
Like the curves, where it's curving around the sprocket.
Like between the two chains?
Yeah, that's like, yeah.
That's at maximum tension.
So we can just reduce it because like that's still full length, so we can like we only need like 3/4 of a link, right? I think was initially, so
Yes.
we can just do less.
Okay. Are you milling, like, did you say you're doing the manual mill for the sprocket, or you're doing out the center hole, or are you actually manufacturing the sprocket?
So the sprockets that we can order in that specific size all come with, it's like the sprocket and then you have, I'm blanking on the name of it, but like the chunk of metal, and like the hub, thank you. We're milling off the hub. Yeah.
Also on the chain tensioner, this is just sort of a clarification, that rod, are the screws threading into that rod, or are the screws just pushing it down?
The screws are pushing it down. They are not threading into it.
Does the rod rotate, or does the sprocket free rotate on the hub, on the rod?
It free rotates on the rod.
Have you considered, are there flats on that rod? And if
Yes.
not, yes?
Yes,
Good.
it's flat there.
Okay.
I had a question about this before we.
Okay.
On my perspective, there is a half a link of tensioning capability.
No. So what this is saying, the minimum and maximum is saying, is that depending on how the chain gets put in, we can either, worst case scenario, we can tension it to a link. Best case scenario, we can tension it to a link and a half.
Well,
What is
technically
the
best case isn't best case.
It would be how, like, when we put it in, right? Where the chain is located, if it is like very, trying to find the right words here, I'm sorry. It is very like laggy, then we would be able to tension it a link and a half. If it is very tight, we'd only be able to tension it a link.
Are you certain that the 0.5 links is enough to get rid of the slack? Because I know that from the chain tensioner estimation, we try to use at least 2 links of tensioning, and having a half-inch link of variation just seems small for the link chain you have.
Yeah, so due to the size constraints of it being in that space, there's been a lot of historical issues with chain tensioners. So being able to tension it this much is actually pretty good because we're able to do it accurately and the chain tensioner will stay in place. Again, the minimum maximum may not have been the best way to present this data for those who haven't worked with the chain tensioner. But we do think it'll be able to fully tension the chain.
Is there any thought, I mean, if we find that we are not able to fully tension the chain, is there any thought about copy and pasting this design, again? And then having 2 sprockets that you push down to have this twice to take up more chain?
I think instead what the go-to would be to place a spacer further out to push down the chain, similar to what happened last year where we put spacers in the chain guard to move up the chain so that the chain tensioner kind of did something in the nicest way possible. So I don't think we would copy and paste the entire system, but that is mainly due to weight concerns. There would be space on that box tube on each side to do that, but we would probably just put in a spacer instead.
Moving to the wheels.
Are there any more questions for chain tensioner? Okay, Hans then roll.
Yeah, what is the chain riding on as it comes into the sprocket?
Which sprocket?
Do you mean like that left, like
The stationary sprockets.
here,
Those two, yeah.
like the material?
Those are sprockets?
No, those are going to be laser cut from an aluminum plate. And so those are just like metal spacers basically that fit in between the chain plates.
Okay.
Well,
Do we have any ideas of ways to increase the tensioning if once this is manufactured, it turns out that we are unable to tension the belts to the extent at which we would want to?
yes, if you look in the top here, it is very hard to see, but there are kind of slots there, so that could be moved back or forward slightly. So it wouldn't be able to tension a full link, but it could still help there.
If we really wanted to, we could get one or two more of the stationary idlers to raise the chain up higher.
Yeah. Okay. Wheels?
Yes. I believe at PDR we were looking at a different filament. What is the reason we had to choose PLA Plus?
The printer that allows us to print the wheel in one go does not have an enclosure. The PHTCF, which is what we were looking at, requires an enclosure for printing.
Are we concerned about the wheel splitting on the layer line if we're on top of a line?
I don't think that'll be an issue. There is definitely a worry about having an initial crack in a Z layer line and then that crack propagating throughout time. But we tested the punching resistance of the wheel, and I don't think that'll be an issue. So.
Here.
With the potentially anneal the wheels, I don't really have any experience with this, but a quick Google reveals that there's potentially concerns about warpage or shrinkage. Is there any concern that might mean that we can no longer properly tension spokes, or that the wheel might no longer match the shape that we want?
Yeah, so I think to reduce the warpage, we're going to do a lower temperature anneal than what's typical. I know for smaller prints in PLA, you do like 80 degrees. We may only do like 60. And then along with that, I think we're also going to plan on putting sand inside the PLA print to reduce that warpage as well. And if it doesn't work, we may just have to either switch the filament to something with a higher temperature resistance and lower strength. But yeah.
We can also print more extra rims before we leave to ensure that if one does get like left out in the sun and it breaks, then we can replace it. Sophia, first.
Yeah, I just wanted to give kudos to John and anyone involved in the design. I think this is really impressive. I saw the video and I was like, no way, it's sick. And I think you guys really saw this vision through in a timely manner. So I just want to give kudos. I think this is extremely impressive. And we only started like innovating on the wheels really like last year. So this is a big step. So I'm really happy.
Thank you.
So if you are unable to find a way to anneal the wheel, whether that is due to concerns with just annealing doesn't work the way you expect, or whether we're unable to find a large enough oven to do the temperatures you need, is that a concern, or what happens if you're unable to anneal the wheel?
We could just be careful in our transit as well. We can make sure when we have the
We
wheels.
leave them in AC.
Yeah.
Yeah.
Okay.
Peter?
So the wheels sort of have a very distinct angle to them. Are all four of the wheels going to be identical, or are two of the wheels going to be mirrored? And where's the mirroring going to be? Is it going to be one of each mirror on each side, or each side will match in mirror?
Yeah, so there are two different types of wheels, right? One is mirrored compared to the other. And so basically the front of the wheel, or the front of the robot will have each mirrored side. Does that make sense?
It makes
Okay,
sense.
so the front two will be, okay.
Yeah.
So you'll have the back one both pointing like this way, the front one both pointing this way?
No. The front will
So
point.
they'll both be pointing like this and then this?
It makes
the
an
front will
X.
point like this.
Yeah, okay, excellent. And then if there are more questions, please.
Yeah.
So 11-inch diameter.
Yeah.
What is that 11 inches to? Is that the floor? Is that the top of the grounders? Where is that?
Yeah, that's to the rim. So the grounders are 0.8 inches. So the total diameter of the wheel is 12.6 inches.
Okay, so it's 11 inches, but it's 11 inches like to the actual floor that's going to be on in contact, right?
Yeah.
Okay.
Hans, you had your hand up a few times.
Yeah, not related to wheels though. Are there any other questions related to wheels?
just wanted to say, I like the idea of making multiple copies and in case someone breaks.
Whatever. What's your question?
Could you provide some more information on the guards for this? That includes like the chain guard, the material, the thickness, dimensions, how it's manufactured, how it's mounted, as well as with the skid plate.
Yeah. So we did not have a slide for that. That is probably something we should have added. The skid plate thickness is 1/8 inch polycarb. That will be made either with water jetting or laser cutting. Both would be possible. For the chain guard, what we will be doing is also 1/8 inch polycarb. That'll either be, again, water jet or laser cut. And then how we will be getting the 90-degree bends is what we discovered last year is if we use a heat gun to heat up where it will be bent and then bend it, we can get much more accurate bends, as well as they don't get like the cracks and little pressure points in them. So we will be doing that process to bend them at the different marks for both sides. Those were the two things. Was there another one you mentioned?
Yeah, where are each of those mounted?
Yes, so okay. So skid plate is mounted. Does the mouth show up on there?
Yeah.
Okay, so the skid plate is mounted to this hole down here, and that is mounted to the front and rear gearboxes. And then the chain guard is mounted to these top two holes. For those of people who remember the Masterlink issue from last year, the screw that was switched out that was too long, it was for top and bottom, but it was the bottom screw that was breaking the Masterlinks. So by removing those holes and making sure that only the shorter screws can be used in that spot, it should completely remove that issue. Alex.
Two things. One, I sent one of the road nuts is 60 thou away from the chain. In CAD, very close. That'll warrant more investigation.
Yeah, I'll look into that.
I sent photos and drivetrain.
Perfect.
The other thing is, so to my understanding, the skid plate, it will run entirely underneath the robot, including underneath the chain guards.
The skid plate does not run underneath the chain guards. The skid plate has a cutout section. I keep trying to point with my finger on the screen. The skid plate has a cutout section here for chain guard to fit in that section. So when chain guard and skid plate are next to each other on the bottom of the robot, they will be parallel. They'll look flat, but there's a cutout section for skid plate. There's chain guard.
Would it be more mass efficient to have the skid plate run the entire width, including underneath the chain guards, and then drop the chain guards to a much thinner material, because they don't have to go and resist the forces of regular or the ground?
That could definitely be looked into for a weight saving way. But for a dust tolerance perspective, that also have to be looked into there.
The stuff I'm thinking of is the super thin 64th inch material.
I don't doubt that it could be weight saving. For how they connect to each other, I might have concerns about dust tolerance, so that would have to be looked into.
Okay.
Peter?
This is about the, can you go to the frame? So it seems like, it's a little bit hard for me to like, it seems like there's not a lot of access holes and like on the sides of the, on the sides of the long box tubes. So have you thought about trying to cut weight saving holes in those sides?
So weight saving holes were looked into for all frame pieces. However, due to, we're gonna look into them again. But the reason we stopped looking into them was, one, there was a lot of other things to be worked on, and two, not a lot of us know FEA, and there was also concerns about properly predicting the forces with FEA so that they don't break or bend. So now that we know weight is very much a concern, we'll look into those again. That'll definitely be something we work on. Access holes were not a concern because of what those different bolts and holes are being used for. We can either reach inside, like easy from the end where these rib nuts will go, or they already have access holes that go through to the other end.
Yeah, I mostly meant because last year we tried to do a lot of weight saving on the box tubes, and we ended up sort of not doing it because we basically have so many weight-saving holes, and so many access holes and bolt holes and whatnot on the frame, that it ended up basically would be exactly the same after we applied the shape optimization. So, given that it seems like there's less, I suspect that at the very least, I imagine we can basically cut big X's into the sides of just every single tube.
Yeah, definitely for these two tubes. The concern with these two tubes while doing FEA was that they technically don't have any forces on them. It's only when like we hit something or there's an irregularity that there will be a moment in those tubes. And there's a lot of confusion on how to properly do that in FEA to get a good result as well. So we'll definitely be looking up like tutorials and more stuff for that. So, or if anyone knows how to do it in FEA, please message me. We can fix that. Okay, Alex, and then I'll.
I don't know if this is a question that should be asked to European Age, but out of last year, at least some wires were run or planned to run through the box tubes. Had that been discussed? Are you still doing that?
That can definitely be done. That hasn't been discussed. If we want to add those access holes with PNH and us can talk about that.
I'll ask the question again in whatever PNH comes up.
Or we can just talk about it and then figure it out from there. Okay. Ocker and then Hans.
Going to the handles. According to the rules, we are required to have at least 3 people to carry the main rod. Will this work with that? Are we able to have a share, or is it going to be too tight for our only have to?
No, people can share.
Yeah.
It might be like, you might be shoulder to shoulder with someone, but it's in a way where it's just there to give you something more solid to grip onto, because it gives you more options where instead of holding it at like the specific angle with like your arm straight, you can kind of hold it up more, which gives you more maneuverability like underneath and makes it just more comfortable for everyone. But absolutely there's room, like you can have 4 people. I mean, you're just, because the bot itself is so small, you're just gonna be shoulder to shoulder.
Also the lengths for these aren't fully finalized, so those can be tweaked for where the different handles are. Like here, it seems like it's very on top of excavation. That could be moved out more, stuff like that. But the concept for them will remain the same.
For the sake of time, we'll take one more question after this one. Mine's not really much of a question, but regarding those on the frame slide, which is 58, the internal boxes and connectors, I mentioned this at PDR. I am still very concerned about the tolerancing between all the components that you are making there, especially across such large components.
I still don't believe tolerancing will be an issue, but when we manufacture them, we will definitely have to be very careful of the tolerancing, as well as in the manufacturing plans, which I know aren't on any of these slides, and I'm probably the only one who's read them so far. Oh, I don't know what I hit. I'm very sorry. In the manufacturing plans, we do leave plenty of time for these to get done. So if we do make them and we discover that there's a tolerancing issue, we can either remake the part or we would remake the part.
One more question, then we'll move on to power and hardware.
Okay. Did anyone else have their hand raised?
Question. What material is the handles going to be made out of?
So the handles physically probably PVC, because that's very easy for us to adjust. If there's concerns about PVC bending, we can look into other things. Personally, I don't think there will be. I've done a lot of very heavy things with PVC pipes, and I've never had them break on me, unless they froze. But that should not be a concern in Florida. Okay. All right.
Thank you, drivetrain.
We got the debate. We are the strongest. The Power Rangers. Power and Rangers. We got the pictures of Homelander. I'm so disappointed. Okay. We also have okay. Hello, we are the Power and Hardware subteam. The basic overview of what we'll be going over is first, I will be going over system architecture, and then we'll be going over our PCBs, and then we'll be going over general box design. So the basics of system architecture is, first to note is that we're using a 10 amp hour battery, which is sized down from last year's. This is good for weight saving, and we did double check with numbers from last year that this will be sufficient for us for main bot. And the main thing to note is that as per regulations, all the power flows through the ESOP and the battery is being monitored through a power meter. Other than that, most of the system architecture is dedicated to making sure that our power is safely and effectively given to all the sub-teams that need it. The motors are stepped up as needed and the Jetson is stepped down. And of course, all the software connectors have been thought about. The first thing we'll be going over is our battery protection PCB.
Alright, so the sorry. The first battery protection circuit we're going over is based on a 555 timer design. It's mostly analog. So basically our circuit protects the robot against undervoltage on a per cell basis, and it's mainly based on a monostable 555 timer. Basically how it works is to get 6 voltages, filter them down to the lowest voltage out of all of them, then test if that voltage is too low to where it would damage the robot if the voltage goes any lower, and it completely stops electricity to the robot through a latching relay, which is seen in the top middle. And in terms of the schematic, we both did design rules checker, which it did pass, and we also did LT spice simulation, which it also passed with it turning off slightly above 3 volts, which we wanted to go for just in case for protection reasons. And we also fully completed our PCB design with 2 full layers, and yeah, that's pretty much it for the design.
So for DFMEA, as you can see, we have a couple of failure cases. Some cases would include the board not getting any power or shorting, which would result in a loss of circuit function. Some other cases would be excessive power to the board, which would just result in the discharging the battery faster than expected. For component failure, just generally, like if the component fails, like if faulty detection or the component just not working, this would also kind of result in a loss of circuit function. But these are all highly detectable and very improbable, and they only result in the board failing, which is not too much of a problem as it doesn't directly affect the robot, it only affects the battery. And as you can see, this is a parts list, so other than the relay, we have a lot of cheap parts that are pretty easy to find.
All right, so this was the secondary design for the battery protection circuit, the BQ TI circuit. Really not much has changed since last design review. Really the main thing was that we finished the PCB routing and we have switched from a power NMOS to a relay switch just for some more reliability there. So really it achieves the same objectives as the previous 555 timer design, but we just think it's a little more streamlined and a little more robust because of the TI chip implementation.
And for the TFMEA, we most common errors we will find are shortage or over current, and these are highly detectable, and the results of this are mostly unable to monitor the robot. More important failure is the BBC, the battery protection TI chip not working, and this is not really detectable, but It is, but the results of this would be not able to monitor robot.
And just really something of note, really quick, is that even in these failure cases, it wouldn't affect the robot too much during competition. It wouldn't affect it at all during competition because this protection circuit is more for during testing than during actual at NASA.
Yeah, and for this battery protection circuit, we would spend around $17 per battery per circuit board.
Right. The teensy breakout board stays very consistent for the most part from year to year. Functionality wise, it's our signal communication for sensor input, for reading from different inputs, as well as outputting commands from the computer. For this year's specific design, we have a couple more connectors and components to be communicating between each other. And so we have some more ports that we're adding, as well as a series of level shifters to ensure that every component is getting the right voltage that it needs. Because of these increased component amounts, we have increased the footprint of the teensy board by a little bit, which is something we'll be considering when we're organizing and arranging all of the boards. Other than that, most of our stuff stays the same as far as the communication protocols we're using, the max chip for translating protocols, and all the previously existing connectors that we have set up. Here's most of the parts list for the legacy board. It stays mostly the same, and a lot of the stuff we have already in-house, which is really, really convenient for us as far as the board that we will definitely be using in the robot.
Just as a quick update on the little side project that we're working on for the custom micro. For those of you who don't know, we're also exploring another option for the Teensy. Well, instead of using the Teensy, we're using the RP2350 microprocessor. And so far, it's just been a project to add more technical depth, and it's served really good educational purposes. I've completed the schematic and have the footprints assigned. Next steps are really just to figure out how to do the layout. There's a little bit more low-level design involved in this, and just to order and source components and figure out what next steps are for software and firmware. And in terms of the DFMEA, this pretty much is similar to, this is the DFMEA for the legacy board, and it pretty much just stays similar. Just making sure that we're sending the right voltage to the Teensy so it doesn't fry anything, making sure all the parts are soldered and manufactured correctly, so we don't have any part failure, like for example, the VSS 138 chip that steps down the voltage to 3.3 volts. But yeah, pretty much standard stuff.
The current sense boards have essentially stayed the same since PDR. This one is for the main and mini bot battery. This is our main design, and it has the same ADC as last year, but we're using the TMCS 1133 Hall effect sensor, which has 115 amp nominal current limit and outputs 25 millivolts per amp of current. And then the differences from last year are that we've added jumpers to allow for variable addressing, which just allows for more flexibility in the case of board failure. And we've also switched to using Wago connectors. This one? This is our alternate mini and main battery design, which is a shunt resistor based system instead of the Hall effect, and we're using the INA 254, which has a 75 amp nominal current limit and outputs 40 millivolts per amp. And then same as the last one, we're using the Wago connectors and the jumpers.
All right, so we also have current sense boards for the linear actuators on the main bot. This is the design that we plan to move forward with. This is essentially the same current sense board as we used last year because it has the same ADC and same Hall effect sensors. It is using the Wago connectors for the power wires, same as the battery boards, and it has we changed the I2C address on the ADC since there will be two current sense boards on the main bot. Otherwise, it's essentially the same board as last year. And similarly, we do have an alternate design using shunt resistor ICs for the linear actuator current sense board as well. We do not plan to use this board on any bot. However, it will be ordered and manufactured just in case something does go wrong with the planned Hall effect sensor based design. This uses the INA 250 A2 IC with a 15 amp current limit. That's really the only difference between this board and the other one. This is our parts list for all boards, for all the total number we plan to make. Which it would come out to around $150 in parts, making 9 total boards. Just to have backups for everything. This could be slightly subject to change since this is assuming we order a lot of components through JLC and have them assemble it. If that doesn't shake out, we can get these parts at similar costs through DigiKey.
And so for the DFMEA, the only thing we really need to worry about is the board failure shorting, which would result in no data being outputted from the current sense. But other than that, all of our cases have a pretty low severity of just degradation of vehicle performance or life. But yeah, that's pretty much it with that.
All right, so the idea for the breakers is just to protect the various actuators and the computers for software from large amounts of currents and keep them safe. The design is mostly unchanged since the last design review, and all of the breakers are automatic reset except for the master breaker, which is a push to reset.
Here's the schematics and PCB schematics for the breakers, and the master breaker is just separate from the breaker board. And yeah, the breaker board schematic PCB is set for high current, so large copper zone fillings and stuff like that. And apart from that, there's 2 breakers and a relay on the main PCB board.
Yeah, so now we're gonna talk a little bit about part research. Basically, almost all of our bulkheads are the exact same, the ones that we used from last year. Almost all of them have dust protection. Most of the things you're gonna see changing is the amount of bulkheads we use. We said there would be a lot more during PDR. It's gone down quite a bit. So there's 2 USBs instead of 4 now. Yeah, not much has changed since PDR, but let's look at the actual box.
All right, to safely house all of our hardware, we settled on a 18-inch by 14-inch by 2.36-inch box design with a sheet metal thickness of 0.0625 inches. In our top level image, we have 4 motor ports, and then around our right here we have our battery and e-stop, and then our 2 linear actuator ports. In the back, we have our 2 USB-A ports along with our 2 D-subs. And then on the side, we have our Ethernet port and then our camera mounting holes right here.
Yeah. And so here is our overall hardware placement sort of diagram thing here. It's going to be a pretty tight fit this year. These are with all the measurements after the boards were designed. But we should be able to get it done. Yeah. Mostly.
And most of the DFMEAs for the box design and breakers have to do with breaker fault. Although we did source our breakers properly, so they're pretty reliable, but of course that'll be something we can detect. And in terms of box design, the biggest concern is of course dust protection, but again, we did make sure that all of our parts are properly rated for that, so that should not be an issue. And again, also very detectable. We will be able to solve any issues that might arise with that. With that, we conclude. Are there any questions?
Yeah, so I had a question about your breaker. Let's start here. What is connected to which breaker?
So each breaker has the same footprint, so it doesn't matter which of the current ones you choose during current soldering. But example, the top one could be for the actuators and the bottom one could be for the software computer.
I'm not concerned about I'm concerned here. What is connected to each one? Are we running all the motors through one breaker? Are we running, I don't know what is running through any breakers. What downstream components are being powered up right now?
It's just both actuators at once because I assume they're both being powered at the same time. And the power to the software computer.
Which breaker is covering the software computer versus the actuators?
Bottom breaker is software. So these two.
Size-wise, the 5 amp versus 10.
Size-wise?
10 versus 15, sorry.
The 10 amp is for the main bot computer and the 15 amp is for the actuators.
For the breakers, is there a reason the main breaker is not an automatic reset, the master breaker?
This is because it was hard to find one that wasn't at such a high current level, and besides, if this breaker were to ever pop, we would have to open the box and fix something because like a wire had to have come loose and short with the battery. So it doesn't matter too much that it is that nature. Yes?
What is this breaker used for and how is it connected?
The master breaker?
The relay, sorry.
The relay?
Yeah.
From my understanding, the relay is connected to the motor controller, and if we ever need to emergency shut down the motor controller, software can send a signal to the relay and shut it down.
Are all the 24 and 48 volt controllers running through it? Are they all 24 volt or the 48 volt?
I think it's only the 48 volt one. Yes.
Last year, we had a relay in the box that was doing this and it had issues. Oh, no, that's sorry, I didn't have it fixed. But it had issues with it tripped permanently. Did you design for that? You did anything on it?
It got tripped permanently, you said?
Yeah, it was unable to release or unable to trigger some one way.
The issue that happened is at competition, we drew so much power to our main relay that we ended up burning out the trace on PCB, ending our run premature because the robot got disconnected from power.
Oh, yes, I remember you sending that. The traces are a lot thicker, as you can see here, than they were in previous years.
I'm not sure if here's the best place to mention, but on this overall layout, there's a motor stop switch. Is that connected to this relay? If it's not, how is it interrupting the flow? What does that motor stop switch do? I've only ever seen it in the schematic, and I haven't heard you mention it otherwise.
I am not sure.
Yeah, no. So that mostly comes from last year. We had something similar in the box, kind of added somewhat last minute. If you remember, that was for specifically just so we could shut off power to the motors, but still have software be able to do what they need to effectively without them on. That's what that was added for. In terms of connection wise, frankly, it depends a bit on manufacturing and how breakers go. As you mentioned, there have been issues with breakers in the past, so we need to do a lot of testing before we can say anything definitive about them. And once that's done, we can do a little bit more. Mostly what that was for is to make sure that we have room in the box for a motor stop switch should we need it, similar to last year. Hazia.
So personally, I just want to say I'm really happy that everything you guys have done with us, habits and PCBs, that feels very clean. I'm just curious, moving towards like application. Last year we worked pretty close with drivetrain on working on bar run pads. What's the plan for that this year?
Yeah. So that's something that's been on our mind, specifically with box design. We made sure that our bulkhead placements would coincide relatively neatly with wiring. I've been in touch with mechanical subteams and the chief engineer on this, specifically looking over the entire robot CAD and making sure that there are wiring paths. Again, most of that was done so that we could have convenient places for the bulkheads for both the motors and the actuators. As you can see, they're designed so that it's the easiest case scenario for us to wire. That has been taken into consideration. I do agree. It's good to work closely with mechanical subteams on this to make sure that we have avenues for that.
Where is the battery?
The battery on the main bot, I believe we decided That's been somewhat of an issue for mechanical subteams and us working on is placement of batteries, but I believe right now we should have it in a relatively similar place to last year, where it's on the side in a little box so that it's safe and not inside the box. The power hardware box.
It's in a very similar location to last year, very similar design where it is, lucky that I did send me, sorry. I remember this very vividly.
Yeah.
So it's very similar to last year, and it will sit on the frame next to that position, right where we need the box.
Correct me if I'm wrong, so are we using a smaller battery and a big pot? Okay, how much does that weigh compared to the battery we're using on the small box?
Off the top of my head, I can't exactly say. I want to say it's in the realm of 300 grams. I want to say. I go more into battery sizing in the mini bot section because there's actually a big issue with battery sizing for the mini bot specifically due to weight concerns. I go a lot more into what the calculations looked like for that, all the considerations we had, all the weights of the different batteries we chose from and how we landed on the amp powers that we have. But it is significantly less weight than the 16 amp hour battery that we were using last year and we plan to use on the mini bot.
So we're using a 10 amp hour on this one and a 15 on the
16. Yeah.
About 700 grams.
700 grams, excuse me.
For the box itself, do you plan to lay out your PCBs and boards in advance? And if so, can we make the holes in the box before we send it to fabricators to make it?
Yeah, so that was something that was brought to my attention by the chief engineer. As you can see, we've begun working out on exactly where things could go in the box. But as we saw from last year, especially if like virtually anything changes with mechanical teams, things change for us very drastically. So things need to be changed around pretty last minute typically. However, if we could get very firm plans from everything, there's a chance we could at least make some or maybe most of the holes, but that also depends on when we're planning on ordering the box. For example, if things aren't confirmed and orders are placed and whatnot before we would like to order the box, we wouldn't be able to do that. But I guess it mostly depends on which comes first, with confirmation or box
Unless
order.
I'm mistaken, I don't think mechanical teams are changing their electronics anymore, right? I mean, we're not changing the motors, not changing the linear actuators.
We're not planning on it, but
So I think it's safe to say that probably it's pretty long.
yeah. I haven't heard.
Some questions from the Slido. Julian is asking whether battery protection circuit will be removed for competition since it isn't necessary for the actual competition runs.
Yeah.
Another question from the Slido. From an anonymous user, they see a lot of undersized power traces that should be zones, mainly battery protector. I wish I could tell you that.
I can, I also have the same concern. On battery protection, to my knowledge, all of the robot power has to flow through battery protection circuit. Not a single one of those traces is sized to carry the 30 or so amps of the entire robot at full load. This one is better. The other one has super tiny spindly traces everywhere. And I am very concerned, as is the anonymous commenter, about your traces burning.
I was planning on fixing that trace. I didn't get a specific size of the traces when I first made it, but I'm doing more research on that. We're gonna make the traces a lot bigger and possibly make the PCB a slightly larger and also have ground plane for to dissipate the heat a lot more and all the power less.
I am more concerned about this when the goes on. There appear to be unrouted traces in the core. You cannot see them from here. If you zoom in on the slide, there are a pair of unrouted traces. I assume those would be fixed. Yeah, at some points. And also, there are two battery protection circuits. Are we using both of them? Are we using like both in series or in parallel? Are we only using one? If we're only using one, which one are we using?
For which battery protection?
There's the 555 timer and there's the BQ series. Which one are we using? Are we using both? Just one?
So we're planning on manufacturing both and testing both. What it comes down to, which one we typically are going to use, is going to be down to testing wise. In theory, it would be the BQ779. But again, we are planning on manufacturing both and testing both, and things can happen during testing that we can't predict, and we might be able to use the 555 timer. But again, that mostly tests on how manufacturing and that mostly depends on how testing and manufacturing goes for both of them.
For the box design, we are required to have external antennas, so I would definitely recommend adding those as we move towards those.
In regard to if we try and pre-plan where all the holes go before we send the photos, with all your alternate block designs, would all the mounting holes on those be same placement, or would we have to plan for variable holes?
Yeah, that is another reason why I might hold off on some mounting holes. I can see the merit in adding some of the more firm ones beforehand. For example, potentially the 24 to 48 converter, we might be able to add mounting holes beforehand for that because we know exactly what we're going to use for that and the dimensions and whatnot. We do, like I said, we do have what we plan to use set, which is the Hall effect for both the actuators and the battery. So if we really wanted to, we could plan for those holes, but to my knowledge, they're not the exact same size. Someone from Current Sense can correct me on that. The Hall effect versus shunt, they're not the same size board.
No.
No, yeah. Yeah, they're not the exact same size. So again, I might want to hold off on that. I was personally part of the post drilling holes last year. Obviously, it is a little bit of a pain, but it's not undoable if we do need to add holes post ordering the box. It's not, like I said, it is a pain, but it is 100% doable. It's not the biggest pressing issue that we would have, but it would be nice to have it beforehand. I agree.
For the sake of time, we'll take one more question.
I have a question about the PNC board. So you mentioned using a 24 volt to 5 volt adapter on your schematics, but you don't mention it here. I assume that is powering the PNC or the peripherals around the PNC?
The PNC is powered the USB cable.
Okay. How are you ensuring that the 5 volt signal from the Jetson and the 5 volt signal from the 24 volt to 5 volt converter do not mix and can never mix?
It should be. The 5 volt signal from the Jetson should be coming through the USB. I believe that the traces are all separate, but I will double check to make sure everything. I appreciate the concern.
That's how we blow up Jetsons.
Yeah, of course. Yeah, I'm almost positive that I accounted for that, but I'll go through and double check to make sure.
Okay. We'll move now on to software. We are currently right on time where we wanted to be. Software should be another 30 minutes or so, and we'll take a break after that. After lunch, we need to take a box. So thank you, Power and Hardware.
Hello, everybody. We're going to get started with software now. So first things first, we have a new path planner.
So the main goal of this new path planner was to work better in the sand. So it turns less, it prefers to take much straighter lines, which works much better with our point-to-point control. It's also much easier to tune. We don't have to do additional processing on it, which saves a little bit of resources. Still needs a little bit of work to prevent it from flipping back and forth between going left, going right, which the robot gets confused about, but it's going very well.
And we're still in the process of implementing Isaac Ross. Right now, we're maxing out the Jetson for video processing at only 240p, and the CPU is at 100%. And so if we implement Isaac Ross, this will allow for higher resolution processing.
Yeah, so right now we've written all of the code that we need for our ROS environment to use these Isaac ROS packages. And we've done that for April tag detection and point cloud generation. And in addition, we've installed most of the files and packages that we need to implement Isocross on both Jetsons, and we have installed some of the tools that we need for certain sensors, such as the RealSense cameras.
For our next steps, we're going to install specific packages, specifically for April tag detection. And we have a few issues with this because the version of ROS 2 that these packages are built upon these won't run on the Jetsons, so we need to alter the file so that it'll adapt to that. And then after we get these installed, we're going to be able to test it with different object detection programs and test the efficiency of the CPU and GPU.
All right, so we're looking into image segmentation for making a real-time obstacle detection model. So far, we've extracted the image frames from the ROS bags from our previous competitions and segmented them. As you can see, the video shows a visualization of the output of what our grounded SAM model detected. And so we have two different models that we are looking to train. Yes.
Yeah, so the two models we're looking at right now is a YOLO-based model that takes in RGB images, and the other one is a depth model that takes in RGB depth images. And so we've been extracting both from the ROS bags, but the purposes of both differ. So for the YOLO model, we expect that this model will be performing better in competition-like environments. However, if the environment is different from the competition, or if there's extreme lighting, it's too bright, too dark, it may perform a little worse. So we are currently working on this model as of now, but after that we are transitioning to the depth.
Yeah, so the depth model is much more robust in terms of what it sees and how it actually annotates and segments and things. First, we're going to work on the YOLO model. We're starting off with the smallest version, which is the easiest to train, it's the fastest, and then we'll work our way up and see whether that improves the accuracy or whether it just needs too much data. And then after that, we'll also train the depth model, which should be pretty consistent across any sort of environment that we have, because from the ROS bags, in addition to extracting the PNG RGB files, we also extracted the depth images, so we can use those to train the depth model.
So this year we're trying to limit our bandwidth, basically from the control room, I guess. And the limit that we've been given by the organizers is 4 megabits per second. And so currently, if you can see the image raw, like the subscribed screenshot, that is well over our limit. So we've been using Fiora compression, which is a library provided by ROS, to kind of bring it down under our limits. And similarly, we've decreased our point cloud resolution to have a voxel size of 5 centimeters, and that'll bring us down from about 1 megabyte to about 210 kilobytes per second. And we're not losing too much or any noticeable image resolution either, which is nice.
Okay. For behavior this year, we're obviously having to redo it all, do the addition of having 2 robots. This year we decided to go with a more explicit state machine, and in that involves explicitly labeled failure states and actions to take when those things happen, all with the goal of consistency and reliability. So essentially, we want to reduce the chance of having to switch out of autonomy, even if fixable errors occur. So this is the labeled state machine for the main robot. It might be a little hard to read up there, but the overall idea of it is the same that was presented for systems ConOps, with some of the excavation states maybe a little bit more expanded for how software in particular will use it. And that is the green. And the red states are the failure states. To go over them quickly, for things like traversal, when we're moving around, there are 3 failure states here which could happen. Those include stalling, losing our path, or getting stuck. And we're thinking about ways to try and solve that or remedy that. There are a few other minor ones that all involve stalling or getting stuck. And basically, the hope is we can transition to those states, try and fix them, and hopefully transition back to the right place without having to ever leave autonomy to hopefully get those full autonomy points.
I will also add one thing just really quickly. So you might notice that if we're under 2 cycles, then we're going to continue our excavation cycles or try to recover from stuck states. However, the idea is that after we achieve like the minimum requirement for full autonomy, if we encounter like a stuck state where our robot is getting stuck, instead of trying to recover from that error, which could cause us to be in a more risky state, the idea is to just stop operation completely and just take our autonomy points as they are and avoid jeopardizing them in future operations.
Looking at camera mounts, we're going to have 3 cameras and 1 April tag on the main bot. There's going to be 2 D435 cameras that are going to be in fixed positions on the robot, the fixed mounts. One of them is going to be on the back of the P&H box facing downwards, and the other one's going to be on the top of excavation, also facing slightly downwards. The mount on excavation is going to move as the excavation moves up and down, so we are working on ways to account for that and do that in software. We're also going to have 1 situational awareness camera inside deposition, looking at the transition between excavation and deposition as we did last year. And we're going to have an April tag on the back of on the main robot for the mini bot to align to, and that'll be mounted onto the gate of deposition.
Okay, so DFMEAs are very similar to what they were at PDR. The main threats to autonomy remain our perception and navigation stack, as well as localization, which is why we have taken such care to think about how we could recover from these errors in our behavior without exiting autonomy, so that we can still gain our autonomy points. So still kind of very similar to what PDR was. So kind of some next steps. So especially with the size of the mini-bot, we think that it could be a bigger hazard for the mini-bot to fall into a crater, which is harder for us to detect and much easier for us to fall into due to the size and us only seeing the back wall. So right now we are working on analyzing the curvature of the crater walls to get a better estimate of the rim, just so that we have less of a chance of falling in. We also need to do testing of our path following algorithms in the sand pits once the weather improves, which should be very soon. And then we're also going to be starting to work on our behavior implementations in our simulation, as well as in person once the weather improves, especially considering our startup procedure within our 2 by 2 meter starting area, our link-up procedure, which will need to be fine-tuned, our excavation cycle and deposition cycles, as well as obviously LiDAR. Now, LiDAR, we are still working on ordering. We do anticipate some work with that. However, we do also have fail-safes in case we run into unexpected issues with the LiDAR, especially considering that we're getting it at kind of a much more delayed timeline than initially anticipated. So that's about all we have for software. Are there any questions? Yes, Alex.
Yeah, so looking through the video that you have for the image segmentation, it doesn't look great, shall we say. Everything is wrong all the time. Are there plans to fix that? What are the next steps for that? And is there what is the possibility and chance that it simply does not work and we have to discard it entirely? And are there plans for that in case?
All right, so what the video shows is any bounding box that the model could find. And so the ones where the entire screen is shown as rock have a very low confidence score, whereas frames where there are actual rocks have a high confidence score. We'll be able to filter out these and train the model based off a threshold where we are a lot more certain that there are in fact rocks.
And about the backup, so yes. So worst case scenario, if this doesn't end up working, we still do have our perception stack from last year. It worked decently well. And we're also still we're still fine tuning what we had last year as well. So we do have some level of confidence that we will still be able to succeed if this doesn't end up working. This is just meant to be it's kind of like a supplement to hopefully improve our perception capabilities.
Sophia.
So can you use the YOLO or depth model for rim detection, or you guys mentioned that was the next step, so it's like you have these different.
Yeah, so the current plan is not to use the models for that simply because it is much harder to see visually. And our cameras are going to be in a different spot compared to last year. So we're thinking that we're going to do that more analytically, trying to detect circular areas that are considered obstacles or semicircular areas, and then fitting a circle and completing essentially the crater.
And then for, linear behavior map for the main bot, I saw that single robot behavior is possible, and it just like, does it have as much computing power as the main bot to do like autonomous pathfinding and fully autonomous operations, or when you say like single robot behavior, do you mean like you have to manually take over some parts of the main bot?
Yeah, so the compute is the same as last year, so it would still be able to perform autonomous actions as it did last year.
Yeah.
And the plan would be that it would fully take over and still continue doing that autonomously. Yeah. Well,
In terms of behavior, are we confident that while we're excavating, we will have enough room to create 7-inch holes and be able to continue to excavate for the 50
yes. So one of the plans that we're working on to account for that is that we're going to try. Last year we started like close to where we essentially the meetup location was, and we moved outwards. We're thinking about reversing that and starting on the outer end and moving closer to that meetup location, such that we would not traverse over a spot that we've already excavated in and would have a less chance of getting stuck.
Okay, my only other concern with that is if while we're excavating, whenever we go back to a similar position, whether or not our crater would be listed as a crater, we wouldn't be able to drive close enough to it to get as much value out of excavating as we can. Is that a concern we have?
So the first part of your question was whether we see it as a crater, right? Whether we see it. So the idea is after we start our excavation cycles, then we just or after we've mapped a sufficient amount of the area that we're going to be traversing in, we stop mapping altogether to avoid kind of some issues that we had at UCF, where we would turn a lot and then create craters that weren't on the initial map. So in that regard, they shouldn't be considered craters. It will just be kind of like a manual kind of keeping track of it in the program.
Peter.
On that though, you say we turn off mapping. My understanding is that quite a bit of our idolatry comes from SLAM, right? Which stands for simultaneous localization and mapping. Can you turn off the mapping of simultaneous location and mapping?
So what we're going to do is we have two different ways. We essentially take the output from the SLAM model and put it into another map that we then do a bunch of processing on to make it look better and make it do all the costs that we want it to do. So what we can do is we can just cut that connection. So it's still going to be doing the mapping. We're not going to save any processing power per se, but we're going to get out. We're just going to ignore any obstacles that it determines are new obstacles, and essentially ignore everything that it's doing now and only do what we had previously.
Right. And then another question is that along the same lines that Will has said, I remember Eric Reiner mentioning that one of the trickiest parts of Caterpillar's autonomy work is planning out excavation cycles and pathing for when they're actually digging out a big hole, right? Actually planning out the cycle, the pathing for finding out that big hole. So it sounds like there hasn't been too much work developing this based on your slides. Is this true? And is this going to be a larger priority going forward?
So in terms of choosing where to excavate, we have the benefit of being in a very controlled environment. Like it's a much smaller search space, and we can kind of get away with doing the simpler option that's more likely to succeed, because otherwise we'd have to worry about a lot more complexities, which could throw off our autonomy planning, that could throw off our autonomy scheme as a whole. So we're trying to keep it simpler in the sense of, okay, just like expand in a semicircle and just keep bringing in material from outside to in, as opposed to trying to like plan, okay, this is the exact best spot for us to mine right now. This is the exact best spot.
Well, previously, Ankur mentioned that instead of expanding a semicircle, making a semicircle contracting in.
Right.
Okay.
Yeah.
That's what we And we'll be looking at essentially going to be making sure that we also don't hit any rocks when we're doing that, but that will be, we're going to essentially just find a line, make sure there's not a rock there, or choose the first point that isn't a rock. Kyle?
There's a chance I missed this because I had to step out for a second. Do you think in the creation of your initial map, since you said that you're turning off the mapping once you've gotten a sufficient map, do you think that there's some issues in creating that map because there's two robots? Do you think that's going to cause interference with creating that map?
Yes, so that's possible. We are looking into, we're looking at ways that we can account for that. either using some models where we can clear out obstacles, so only taking in clear obstacles, or removing any obstacles that are where a robot is currently, because we do know where the robots are relative to each other, so we can account for that. Additionally, the robots are never going to be moving autonomously in the same space, except at the very beginning. So they, even if it does detect, even if the mini bot detects that the main bot is there, it never needs to actually go into that excavation zone at all. It will only meet up and just touch each other, which will be handled without looking at obstacles. So they will never need to fully cross and would have a planning issue because of that.
What is, so how do the robots know where each other just from your video? Is that how they know where they are?
So they both do their SLAM operations, and we've been looking into ways to kind of like unify that map so that they have like the same reference points. So they will always know kind of where they are in relation to each other by knowing where they are on the global map.
And we have April tags. We're going to have 2 April tags, most likely, on the corners, the inside corners of the starting zone.
And then it's like how is the accuracy of that map? So you're I guess you're going to map at the beginning, right? How is the accuracy as you get farther away from the point of mapping? How does that vary?
Yeah, so the accuracy should be still pretty good. We are expecting that it would be fairly accurate, especially since we are properly doing SLAM this year and we have ability to go back. Essentially, what it'll do is if it sees something that it's already seen before, it'll be able to go back in time and grab that position from where it was before. So it knows it can reset itself, and since it's saying it's such a small area, it should be able to fairly accurately do that, and it won't, since it's on traveling, not seeing a lot of new locations, it should be able to stay within the same area.
One more question. The camera mounting, how, you have one on the back and one on the front.
Yes.
Where are your blind spots?
Yeah, so the blind spots would be on the the corners essentially. We don't expect this to be a major concern with this robot because this robot is going to be staying in the excavation zone where we are allowed to essentially hit the obstacle. We don't hitting the obstacles doesn't lose us points as it would with the traversal. And additionally, it's going to be moving fairly slowly. It's not a very fast machine. So we wouldn't be concerned about turning into an obstacle and going very fast into it or anything. Yeah.
So the LiDAR is taking a long time to arrive or something, and we haven't ordered it. So have you ordered it? Is it taking a long time?
We had issues related to previous time.
Okay, so given that we don't have this LiDAR yet, are we going to use it on this year?
We still anticipate that we still are hoping that we will be able to use it, but we are not relying on it, and we'll talk more about that. LiDAR is actually only going to be used on the mini.
process. Curious what that looks like.
We were talking about this basically last night at the CDR prep. I think it was sort of an open question to the general team. Would we rather stay in autonomy and try and get the full autonomy points, right? Or would we rather go for probably maybe more effective human operation, right? So maybe they can correct me if I'm wrong. I think it was maybe going to be phrased as sort of an open question to the rest of the team and get their thoughts on that. So whether that's autonomous, Mr. Manuel.
Well, it kind of all depends on how much extra material we need to move manual and manual. However, going through the picture model I went over earlier, I do not foresee us making it to 100 points. We can use going out of autonomy with the extra volume by just using one robot. I think that with one robot design, we should shoot for about 150 points in volume, just totally. So if we could stay autonomous, I think that's
It's our strong suit. To stay autonomy, and every time we restart it, it's actual autonomy, the robot and all that was occurred.
I would say that given we already have some pretty good, I think it shouldn't be too hard to try to do some more sort of score prediction work in terms of like a detailed analysis of we've already accomplished this. Is it worth it to get out of quantity, right? Like if we've already got full cycle, then the answer is probably yes, we should have, then probably no, we should not get out of quantity, you're crazy. But if we've only gotten like halfway through the traversal zone and it starts spinning around, then probably the answer is yes, we should get out of quantity. We haven't got. So I think it would probably behoove us to do some like pretty preliminary analysis and print out an explicit flow chart of this is the state where this is the decision we should make. So that in the control room, if/when something could maybe go wrong, we don't lose any time in discussion. We just look at the flow chart and we go, this is the state, we have to do this, we've done this. Yes, thank you.
I think this would be a great thing to work with systems on.
Any other questions?
So what is this weight removal on this main diagram? Is the main model is fully stationary during that position, or is it actually working with the move on to guided?
We'll have a lot more details on that when we get to the minibot section. Basically, the link-up procedure, when they get close together, we take a lot of steps to make sure they are not moving at the same time because we really want to avoid that so they don't hit each other. And yeah, there'll be more details.
A question from Eric Reiners in the chat. What is the location accuracy between the two bots?
That is still yet to be tested. That is still something that we have to work on with two separate systems with testing that. But hopefully coming soon.
One more question about YOLO. We know that Jetson is fairly limited in terms of processing power, as you have demonstrated in isoproc and also just many times incrementally. Where do you find that processing power to go and number a YOLO model onto?
Right. So Isaac Ross actually has packages to run YOLO models and to run machine learning that people have had some success with running on a Jetson or a Nano. So we were kind of using these as kind of like, oh hey, if they were able to get it working, why not see if we can? I mean, obviously it's still up in the air and will still be like dependent on our final testing. But that was kind of the impetus.
And also, the minibot would be doing the primary mapping of most of like the obstacle zone. So it has a much more powerful computer. So that is where the processing will likely go. That's it. I think we're done. Hand it back over to Hans.
Thank you, software. Okay, that concludes our main bot section of our critical design review. We will now take a 1 hour break for lunch. So we will resume, let's say at 1:30 p.m. Eastern time back here. Thank you to those who are here in person. We hope to see you back. And thank you to those who are tuning in online.
All right, we are back a little bit late. That's okay. Let's see, we have the Slido again, same code. But if you are joining new online or new in person, I don't know if there's anyone new here. This is the link for Slido. Q&A is same, brief overview. Please make sure to put your name. Don't put anonymous. If like we need to follow up with you, or if it ends up being too long, we need to ask you after. It's much easier to find you if you have your name. On a similar note, just like not Slido related, but if you're talking up here, we don't have the mic, talk louder, please. I'm like over there, and sometimes I can't hear you. That's probably people who aren't here right now, but like talk louder. Especially for questions, because it's like trying to write stuff down and being like, I heard about half of what you said. I do not know what you were talking about. So links up there if you need it, code to CDR. Start with a high level overview. I feel like we should have had, agenda also is just same subteams, except starting with deposition.
All right, so now we're gonna begin our session over the mini bot. So with a high level overview for that,
is just gonna be basic dimensions and mass. Currently, the mini-bot system sits at 0.429 meters length, 0.692 meters width, and 0.577 meters height. And right now, its mass is currently sitting at 28.85 kilograms. Any questions about mini-bot yet? I assume not. Okay. All right, deposition.
Hello, everyone. We're at deposition, and we're back to talk about our mini-bot system. Mini-bot system is largely the same as main-bot system, so there's not as many slides this time.
Yeah, so the dimensions kind of vary depending on if the door's retracted or not. So the retracted dimensions are around 14 by 19 by 11 inches, and then when it's extended, that length goes up to 17.9. It can hold up to 31.2 liters when filled, which is a little more than the main system, and takes around 2 seconds to deposit. And then the overall weight is around 7.1 kilograms.
So as mentioned, the deposition system has a flap, which will extend at the start of the match. So the flap is going to pivot around at the front to fold open and expand our carrying capacity, and also make it. So as you can see here, right, this is it. This is it. The flap retracted. So this is how the robot's going to start, and then a rubber band will pull the flap open into this position, where it will remain for the rest of the match, following a 68 degree arc, and it's going to end 45 degree outwards. This does a couple of things for us. It increases our storage capacity. It also lowers the receiving level, which means that we can make the main deposition a little bit less angled, while still being able to sort of keep plenty of regolith in, right? And this piece here is currently planned to be made out of a bent piece of aluminum.
For the DFMEA, this mostly just deals with the flap and possible issues with that. We're not too concerned with it, seeing the RPM being pretty low in its values. It's mostly like if the rubber bands fail, or if like the door breaks somehow, or regolith gets somewhere where it's bumpy. And it's kind of the similar things we've talked about in the main deposition and how we mitigate that.
So our priorities moving forward are, again, with just like the main system, is to just implement any feedback we get from today, and then prepare for manufacturing with like the drawings and things like that, and then just ordering parts and assembling.
All right, are there any questions? Emily, yes.
So for the first slide, where it's rotating around, the curve is cut inside of the ball.
Yes, sorry, that's an old rendering. The curve, yes, the curve, this rendering is slightly old. We made this change last night. There's also only a curve in one side, so.
No,
there
it is on this. It is
Anyway,
on this.
yes, the curve will be cut into the flap itself.
Okay, so it's the second slide that's accurate.
The second side is accurate. The rotating rendering is inaccurate with the slot. Yes, thank you.
Then I just look.
Okay, Ankur.
Where does the elastic band go from?
So
it's not depicted.
It's not really depicted. The elastic band is going to go basically from like sort of down here on the flap to the pivot point.
Which
one?
one?
On there to make that happen.
Yes, there'll be like a bolt basically. So a wrapper.
Like a.
It's just going to be literally held in. It's going to be always trying to be releasing. It's going to be held back by being next to the main robot. So literally, it's going to be the main robot deposition system, which is going to hold it closed. And as soon as we drive away, that obstruction goes away and it'll fold out. Yes, Alex.
So testing, we found the regolith shifted like inclined surfaces.
Mm-hmm.
I'm concerned about dumping the regolith onto the flap and it just sticking on the flap and not getting down to the conveyor.
We are not concerned about regolith not getting down the conveyor. We are slightly concerned about regolith staying on the flap and not being fully removed.
Have you considered slippery coating or something similar?
Yes, we're looking into those. Similar to what we're looking into for the belt. Yes.
Is there concern about the rubber band breaking?
There is concern. This concern is planned to be alleviated by replacing the rubber band before every time we test and every match. Rubber bands are very cheap. So we're just going to replace it every time and we'll be fine. Yes.
do you know what type of rubber band you need? Is it just like the standard generic ones? Do you need a big beefy one? Do you need a long one?
We probably need a pretty beefy and a fairly long one. We don't have that explicitly picked out. I have some big rubber bands from the Purdue bookstore that I use, some big latex ones. So we can try those, or we can try to get bigger ones. Either way, I imagine there will not be much concern. Yes.
And are you concerned about the flapping around because it's being held open by this rubber?
So once we get any actual material in it, then it will not be being held up by a rubber band. It will be being held up by the weight of the regolith on it.
And the center of the gravity will now be like having the door to stay open rather than trying to close.
So assuming that the robot doesn't pitch forward violently and fall into a crater, then it'll probably stay open. And if it does do that, there might be larger concerns. But good news, once it comes into a crater, it has to go out of the crater as well. So then that reciprocating motion will pull it back open. Any other questions? Yes.
What material is the flap made of and how is it manufactured?
Flap is made out of aluminum, I think 16th-inch aluminum?
Something like that, yeah.
So 16th-inch aluminum, and the plan is to laser cut and bend it. John?
Have you guys done any testing on the interaction between the two deposition mechanisms?
No.
No.
We've, to the best of our can, we've looked at it and it should be fine, but no, we haven't done any sort of testing like that. The hard part of that is that we only have one deposition system right now, so. Alex, yes.
Regarding that, when the flap is open, does it go underneath the deposition system, or what is the alignment of the two systems?
Slightly underneath the deposition.
Go to the. What?
Yeah. I believe the flap is underneath the deposition system.
It's like at the corner.
If this is the one of the first couple of slides show this. I'm not going to flip all the way back there, but the flap ends up sort of aligned with below the top of the other valve, which should help with the transfer as well.
Slide 23 for
Yes. So slide 23. Thank you, Emily. John?
During transfer, did the two robots actually touch each other, or is there a gap in between them?
There should be a gap. I don't think they should be touching each other. If they do, I don't think.
Hit, then the bots hit.
Yeah, if the bots hit, I don't think it would be that big of a concern.
No.
Well, yeah, John.
Does the flap act as a kind of bumper? Like if the main bot were pressed against it, is that retract up?
It probably would, yes. It depends how.
The flap has been when that flap opens enough, it's at an angle in which it shouldn't come back in the same way it started. If that makes sense.
Yeah. Yes, you.
So the rubber band is keeping it closed or open?
Open.
Open at the 45 degrees.
Yes.
So in what instance would we need it to be closed?
At the start of the match to be within starting volume requirements.
Okay.
It lets us get mini depth kind of under main a little bit, and it just brings our bounding box a little bit.
Yeah. Yes. So for anyone on the live stream, the question was, when do we ever want the flap closed? The answer to which is at the start of the match so that we are within initial bounding volume conditions. And then it expands out and remains open for the rest of the match. Are there any other questions? All right, perfect. I believe that concludes mini bot deposition system then. We move on to the drivetrain system.
Did one of you fall? No, it's just So overview for Minibot, some post PDR changes, but the overall system should look fairly similar. The major ones were the tread design was updated. There was a redesign of the tread tensioner due to concerns that were expressed during PDR, and the adjustment of the frame location as shown. One thing I wanted to point out because of the battery questions that came up later, This is where the battery will be going on Minibot in frame.
So this is our frame for the Minibot system. Overall, the dimensions are listed. It is using the same frame connectors as main. You can, within the smaller box tube, you can kind of see this one through the cutout for the battery. The main difference with this between mini and main is that our gearboxes are included within our frame, as you can see with the taller 2x3 box tubes. This is just, as we don't have a lot of as we have significantly less space to work with, we were like, let's just put it all into one, just have those be taller and it can work out. And as for those gearboxes, as before, they're embedded within the frame. Internally, it's a 1-to-1 gearbox ratio, while externally, there is a 10-to-1 gearbox connected directly to the motor, this bit here. From this, we get about 120 newtons applied to the ground, which is quite a bit more than last year, and then regular 12-millimeter diameter drive shaft.
So this is what the tread assembly looks like in Minibot. There are a total of 52 treads. Each tread has a pin that connects to another tread, and each tread also has 2 bushings, which makes a total weight of a little over 1.6 kilograms. In relation to the individual parts of the tread assembly, the driver, which is this sort of sprocket right here, is based off of a number 50 chain, just with half the amount of teeth on the sprocket, and we're gonna make that in-house. The idlers, which we are calling, which are like these 2 wheels, they're gonna be 3D printed in PLA. They have a diameter of 2.71 inches, and they're about 3 inches thick. And then the tensioner, which is attached to this back idler, is gonna be bolt tensioned. As for the individual tread pieces themselves, they're going to be printed in PAHT carbon fiber with 15% infill. The rods that we're going to use are 2024 aluminum rods, and then we are using 841 bronze bushings, 2 per again. The reason why we chose PAHT carbon fiber is because of its high layer adhesion compared to other carbon fiber filaments, and also its strength, which we want to have in case we have any collisions on the playing field. And then using carbon fiber to increase the surface hardness and wear resistance against things in the playfield.
So we're going to have a set of handles for the Minibot too. And the Minibot, it would work the same as it does on the main bot, where you have these 2 handles. One straps onto the front frame, box frame, and the other one straps onto the back box frame. The only difference is for this one, there's like a small slit in the skid plate just so we can get the strap around. But like, again, just small enough that a strap can go around it, and which actually helps with our weight reduction issues.
So for the DFMEA, very similar to main bots. Again, the 2 biggest concerns here are screws failing and the skid plate. The tread numbers actually work out pretty well. Anything that has a big issue will be easy to see. And so the similar solutions were taken as main bot for this. Plan moving forward, implementing any CDR advice, working on different weight saving, especially in frame pieces, ordering stock, manufacturing, and assembling. And the goal is to have Minibot drivetrain assembled before mainbot drivetrain is assembled, so that with treads we have time to figure out if there's any other issues when we are working with those. Any questions? Will had his hand up first.
When it comes to essentially the treads, is this something in the process we're going to take off the treads for, or is this going to be done with the treads on?
Treads can stay on. How it'll work is we'll have this bolt here in this nut. So we'll have to take off the outer plate and then tension them, and then it'll be fine. Yeah.
So I guess this is just confirming, we have access to a printer with an enclosure to print the treads.
Our printer can do that.
We do. We do have.
Got it.
We do. So I'm wondering if you take pH, TCF was that it had a very strong layer adhesion for a CF filament.
Yeah.
What is the non-CF variant of that filament, and is it a better filament for us?
Yeah, so these are compared here with PLA. So PHTCF is only slightly worse layer adhesion than PLA, but if you look at like PET-CF, that is much worse. Same with PLA-CF.
My point is that looking at PLA and PLA-CF, PLA appears to be just a little bit weaker than PLA-CF, especially in toughness and layer adhesion. So what is the non-carbon fiber version of PAHT? Is it PA? Like, I don't know what the filament is.
It would be PAHT. If we didn't want to do PAHT-CF, we would just do PLA or something. Like we wouldn't do PAHT.
Why not?
Um,
My point is, why add the carbon fiber strands?
yes, that is because for the added toughness with impact strength, this was a concern if we hit anything.
It drops toughness. Added PLA.
This is PAHT-CF, this is PLA.
Yeah, right. So look at PLA versus PLA-CF.
Yes.
Adding the carbon fiber drops your impact strength.
No. Where are you? Oh, you're looking, that's layer adhesion. If you look at toughness,
So first line, fourth column, and then first line, fifth column.
that's PLA-CF.
Yeah, so his point is that you've added carbon fiber and now your toughness is lower than it was before.
For PAHT, adding the carbon fiber makes it better. I will.
Do we have numbers on PAHT?
Yeah, if you go into Bamboo, this is from Bamboo Labs. If you go there, you pull up the filament, you can compare them. This was a comparison done. We didn't have PAHT in this comparison, so I don't know the numbers off the top of my head, but we did look at them last night.
The only thing that I've been able to find is PHTCF when searching for that. I think PA may be the closest material.
I can find it after this and send it in the channel.
My concern is that carbon fiber filaments are generally more expensive and also worse. Looking at these numbers for between PLA and PLA-CF, which is the only fiber filtered to full filament that the comparison we have here.
They're worse in some categories, but in others they're better.
They're worse in the category we care about.
I
Sure to say that we don't care about
disagree.
stiffness or strength, right?
Yeah.
So,
That's fair. I care more about layer adhesion than thickness, though. I think.
I think the issues with layer adhesion by PAHT-CF, which is what we're comparing, and if you compare it to PLA, it's only slightly worse in layer adhesion.
Yes.
Also, the orientation on which you 3D print things can, like layer adhesion heavily affects that. And we have already messed around with having the tread pieces be printed in different orientations to avoid breaking points. The issue that we're at is with our testing, we have only we print it, we take it outside and we jump on it. That's not very realistic for how it will be tested. So the thinking is to print a few of these, put them together, and then test them, run into a rock, stuff like that.
We can talk more later. My point is not comparing, is not saying don't use PHTCF, use PLA. It's what is using a third filament fiber, the PA or PAHT.
Yeah, we've done a very deep dive on this before. We did another one last night.
I'd like to see the results.
Yeah. Okay. John?
Go to slide 124. Are there concerns about the robot, the mini bot tilting over during retina transfer? Because it looks like the wheelbase is very forward compared to the mini bot. And if there's a lot of mass rearward, and it accelerates forward, the mini bot tilts over.
Yes, so that has been expressed by multiple people multiple times. The center of gravity for Minibot is pretty in the center. The reason they are offset like that is so that the angle of wraparound around the treads stays large, or around the sprocket, stays large. and the motors in the frame, we cannot shift that axle, this one, we cannot shift that this way more. Oh, yeah, we can't shift it more this direction. We just don't have space. And the way they're mounted also does keep a lot of the forces closer to the center of the frame. So from a tipping standpoint, it could be an issue, but looking at how center of mass and everything work out overall, it shouldn't be. Yeah.
If you go to your first slide, you have the battery mount.
Yep.
How is the battery going to stay in that box?
A lid.
Cool. How does that mount attach?
There are 2 holes right here. This battery mount has like 2 pieces sticking down, and you just slide a screw through.
And that's on the outside of the frame, or like inside the box too? Inside
the box tube, so you can see here,
Yeah.
it just goes inside here, and then you just slide a bolt through.
So how do you lower it back? Are the tabs the whole thickness of the box tube?
Yes, they should be.
Because they're not in the cab.
What?
Because they're not in the cab.
I'll fix that.
Cool.
Cool. I think that got fixed and then maybe not stored, so. Okay, well,
In terms of the sprocket and treads, in terms of the key shaft, I know that excavation has to switch off the key into an X shaft due to sort of the key breaking through the forces. Is that a concern you guys have?
it's not, due to the gear ratios, and the torques exerted by these gears, it's not a concern to have with treads, at least of what we've seen so far. That's a good concern.
Can you run the keyway shearing analysis on that?
No, but the torque,
You know what you have to do?
we can run that on there, but comparing with the numbers of torque from last year to what's in this gearbox, it shouldn't be an issue. We can still run math on that. Andrew?
Question from Slido from Julian. For the tension sprocket, this is also kind of a similar question to earlier, but for the tension sprocket on the treads, how is it held in place? Is it only being held by the tensioning bolt?
The tension, does he mean, is this what's pushing it forward?
I believe so.
Yes.
Is it held in place by anything except that?
Yes, there is an axle that runs through it where you can kind of see it here where there is a slot in that plate on both sides. So it's constrained in that direction as well, but pushing it out is just the one bolt. Yep.
Speaking of this tensioner, are you concerned, so you said you have to take off that side plate, right?
Yes.
Are you concerned about things moving? Because now instead of being constrained on 2 sides, that's only constrained on 1 side. Are you constrained on the actually like moving or bending? They'll make your tensioning different when you have that plate off.
I think that is a good concern to have. I think that would be easy to fix and adjust for. You're like, okay, when we take it off, it gets a little more slack, so we just need to know how much to adjust it by.
Would it be easier to have like a little window that is covered up with something?
I don't think it'd be easy or possible to fit both a wrench and an Allen key into the window to adjust the tread tensioner easily, because you have to have both to adjust here.
Why?
You have to hold the nut in place and move the Allen.
Wait, so is there a nut on the other side of that plate?
Yes.
Okay. Oh, okay.
There's one on the other side.
Yes,
No, there's not. There's just one.
There's not?
No.
Wait.
You need to have 2 though, so we'll add a second.
Wait, why not use something like a rib? No. Well, yeah, why not use something like a rib nut through that plate?
Yeah.
And then just thread the single bolt.
Why not use a roof nut through the plate? Sorry. Why not use a roof nut through the plate and then thread the single bolt through?
So you have plate, rib nut through the plate.
Yeah.
And then your bolt just kind of threads into and out of that thing. So you need to get a wrench and thing that you use to allocate.
Yeah, that could work well. And then we can look at doing a window. We might have to move this standoff, but we'll look into that. I think we didn't look into that originally because the shape of this was different, so it was mainly taking it from the old model. So that was good. Yeah. Any other questions? Yep.
On slide 117, the overview for the directory system, the mass is about 14.5 kilos, which is about the same as it is on the main plot. What is the driving cause behind the increase in mass despite the smaller space?
That's a good question. So, a couple different things. The motor assemblies on Minibot are heavier because the motors for Mainbot are built in with the planetary gearbox. These have them separate. Another thing is so these side parts of the frame are 2x4 box tubes. They are going along the entire side, whereas in Mainbot, there's less 2x4 box tube, but you do have the other box tube, so I'm not entirely sure how much that would cause it. The other thing would be, so frame is about half of that weight, and then treads are actually fairly light compared to what we were expecting. And there's not any more weight saving that can be done with them. However, with frame, we are looking at doing weight saving holes in them. We ran into the same FEA setup issues as we did with main. Now that it's been confirmed that weight is a big issue, we will look into doing those for both main and mini. I forgot to mention that earlier, so that's my fault. Yep.
The wheelbase looks really wide compared to the length. Do you have any concerns about maneuverability due to it being kind of not ideal geometry for that?
Having it wider is better for turning than having it narrow.
And then you said that the center of mass is in the center. How high up is it? Because that's what impacts your actual tipping.
Yeah, so the center of mass, the clearance for Minibot's about 3 inches. You can see all decimals on there. The center of mass, I believe, Andrew, feel free to correct me, is about here. It's like in the middle of deposition with no regolith in it.
Do you have an estimate of where that center of mass would be with regolith in it?
We can get one.
Yeah.
Because that's what would really matter for tipping. Because since it's so short, I would be since the wheelbase is so short and so wide, I would be very concerned about it potentially being able to just tip over on like a pretty shallow incline.
I think that's a very fair concern that a lot of us have with this. It's not entirely clear what or if there's a solution to that, but we can look into more calculations about the center of mass with regolith and the types of angles that can go up to see if there needs to become a solution for that. So,
Just to give you a specific number, right now the center of mass is about 19 centimeters above the bottom of the treads.
And how wide are the treads?
Like how wide are the tread pieces?
Like what's the length of the treads? Center to center on the bottom, probably.
What's the width of the robot? Is that what you're asking? Length. That would be 13.
Total base of the treads is about 60 centimeters.
Yeah.
It's 60, the center of mass is 19 up. Say it probably will move like 25 or 30 with a whole container regolith because of how high all of that is. So that would be just straight, I think 45 degrees no tip. But I might be wrong on that, depends on, it might be shallower than that because the back end of the treads are closer. Like how far away is, like what's the closest center axle to the tread to the center of mass? And that's what's gonna be your tipping risk.
That
The
is
center axle, the tread?
Yeah, like the center of the axle.
this.
That's gonna be what you're pivoting around.
Okay. So like this to the center of mass.
Yeah.
Those are probably
So
like,
that's gonna be what causes your tipping angle.
Andrew, do you have the CAD pulled up?
We can probably talk about this more in depth later, Kyle.
When I can also have the CAD pulled up would be very helpful. Yes.
Question about the handles.
Yep.
So it looks like you're wrapping something this way around the box tube, correct? Like the box tube is like front and back. Yeah. So how does that work with attaching a tube that's also going front to back?
So the strap goes, so the tube is flat, right? So it's like the full, like think of like a PVC pipe.
Yep.
And then it's like cut in half. And then that half bit goes on the bottom side of the robot. And then the strap goes around from like a keyhole in the pipe. And it goes around that flat bit and then over the like top of the, like through and over the top of the box tube. And then attaches and tightens like back over here.
Are you concerned about the pipe slipping out?
There was some small concern about that, which is why the design was adjusted so that it's underneath, so that it shouldn't slip out. If there's further concern about it, it was also discussed putting like a little plate on top of it, so it's even more like.
We can also like glue the strap all the way like to that flat piece.
Yeah. The concern that I had was this is that if someone picks up the rubber and pulls a little bit on it, will the entire strap, will the pipe slide backwards?
No. So
What is stopping?
there's a whole, like the strap is going through the pipe. Like, I don't know how well, like right here,
Yeah.
this is like a hole that's going through the pipe. So the strap is threaded through the pipe and then through the robot.
Oh, okay.
So like as long as the strap stays around the robot, the tube's not going anywhere from it. Because it's like a charm on a necklace,
Right.
you know?
Okay. And are you concerned about, so your pivot point is fairly far away from the actual attachment point. Are you concerned about the handles getting folded inward like this?
That would be a PVC specific concern. If.
I'm just getting moving away from the bottom of the robot, not even that.
Oh, yeah, okay. That's like part of the strap. So being able to tighten it fully, which we've already designed for, it shouldn't be an issue. Again, it's also flat. So when you tighten it, it just like compresses it to that point. So no, that's not a concern. Yeah.
You haven't asked how long it takes to take on and take off these straps.
Not exactly, but the idea,
I think.
the amount of time it takes you to.
Do this, I think, I'm just gonna say I would like to see a few iterations of it.
Yes.
We can find out what the best result is.
Yeah.
And then we can get actual estimates and stuff.
Yeah.
The idea is that you just thread it through and then there's an interlocking buckle. So you just like click it and then pull it tight, like backpack
It
strap.
would at most take a minute more than clipping it on.
If possible, one of the questions, I would like to see the full belt path, because I find that very hard to visualize right now.
Yes, it's doing belts in CAD is very fun as excavation could probably tell you. So
Even if it's like a side view that is and someone takes a quick
we'll
response.
do like a sketch. Yeah. Okay.
So does the strap go from one PVC pipe to the next?
No, the strap. Okay, so this part of the PVC is one object. You have one strap that goes around here. You have a second strap on this side that goes around here. Where they go on the frame has been highlighted in red. So it's 2 straps for each like handle bar.
So it's 4 total straps.
Yeah.
I don't think so. Okay. We have a question from Max and Slido. What is the load transfer path from the treads to the frame? I see a few bolts into the inner side plus sprocket shaft. Are there concerns for buckling or warping?
Buckling or warping of the tread mounting plate?
Yes.
Yeah, there were concerns for both of those, which is why it's a 1/4 inch thick, even with the weight changes we were trying to do, which is why it's going to look at doing FEA in those plates to see if it's possible to get weight saving holes, because that will have much more of an impact on weight than thinner plates. It was looked at changing it from a 1/4 inch thick to an 1/8 inch thick, but it's not. It's believed that that will buckle or warp, which is why it's being left at 1/4 inch thick.
One suggestion, and this kind of goes for all mechanical teams, but if you have a thick piece, especially metal, you don't have to do a full hole through it. You can just shape it down to like half inch or half thickness.
Yeah.
So that way you can still retain some of that full strength.
Okay. We'll look at doing that. Yes.
Building on that question, how is, so my understanding of the tread assembly is you have outer plate, tread stuff, and wheels and treads themselves, and you have backing plate, and then you have frame.
Yes.
How is that backing plate attached to the frame?
So the mounting plate is attached to the frame with these 4 holes, which can be accessed when you take off the outer plate. So if you wanted to pop off the entire wheel assembly, you can do so just by taking off those 4 bolts. And then I don't think we have a great picture that shows it, I'll be honest.
Do you think those 4 bolts are strong enough to hold that on? And or adding more bolts mean that that side plate has to take less load and can dump more load into the frame itself?
I don't think adding more bolts will help because of where those 4 bolts are located on frame. Like where those bottom 3, these bottom 2 are here, is right here. So you wouldn't be able to add any bolts lower. I think that's the only other spot. If you could add them lower on that tread mounting plate, that would help with load, but you can't attach that to the frame. So it's a moot point there. But
Could they be attached more off to the right or something?
no. Yeah, that's because of how this is designed. You could do another flap out to here.
Could one be hiding in between the tensioner sprocket and the drive sprocket?
What?
Could you put a bolt in between the tensioner right there?
We looked at doing a standoff in that location. You could probably do a bolt in that location if you wanted to. That could help with forces, but I still don't think you'd want to decrease the thickness of the mounting plate just by adding that one screw.
The only, I'm trying to think, is that that would have almost half an inch of aluminum between the box tube and the mounting plate. They're back to back to each other.
Yes.
Which is a lot of aluminum. Like,
It's 3/16, or not 3/16, 5/16.
what is that?
Wait. Math. Yeah. It'd be 3/8.
But 3/8 is still a lot of material, and to my knowledge, very little on the road, but it's that thick.
I think we'll see a lot of forces in this area if and when the minibot hits a rock or any obstacle.
More than the main robot drivetrain frame?
Main robot drivetrain frame is different because of how it's mounted on. The gearboxes are mounted on.
That still seems like a lot of material, and I understand there's a lot of forces, but doesn't warrant being, I think, the biggest material that we have on the entire robot.
It is definitely the heaviest single plate in minibot. I think it does warrant it, but yeah.
That is, I believe, a similar strength to excavation mounting, which I've also been looking at.
Like a conversation for later. There's some notes and one follow-up.
Yeah, if anyone wants to follow up with this, just message in drivetrain or me. So, any other questions?
Hello, we are Power and Hardware. So Minibot is relatively simple for us because most of our boards are direct duplicates from MainBot, so we won't be re-going over them. The main things we're going to be going over for Minibot are system architecture, and then some extra hardware considerations such as battery calculations, and then we'll also be going over box design because that is also different from MainBot to Minibot. You can see there. So the system architecture, the main difference here is the lack of actuators, the computer change, and also the fact that it's 16 amp hours rather than 10 amp hours as it is on the main bot. And I'll get into the in detail reasoning why as a moment. But for the time being, again, the main purpose of this is the fact that all hardware and all components get the power and communications allocated to them safely and efficiently. That is the main message here. And so extra hardware considerations is another battery, which is again 16 amp hours here, that adds more weight and also more expense to us. Another box, again, that's more weight and more expense that we're going to have to, we have considered and have put into the budget. And then more bulkheads and connections and wiring. And again, we do duplicate all the boards. They're going to be the same between each bot. Of course, there's no current actuator current sense because there's no actuators on mini bot. And then the breakers, the breaker design will remain mostly unchanged, except for the two 15 amp breakers for mini, and then there's one 15 amp and one 10 amp for main. That is, I believe, the only difference between the breakers between them. So as mentioned, this is a more in detail explanation of battery sizing. So we used last year's data and we adjusted for this year's needs. So the main watt hours came out to about 109 and the mini watt hours came out to about 272. And then the main amp hours, including air, came out to around 8, and the mini amp hours, again, including air, came out to around 16. So we did consider using an auxiliary battery this year to save on power. However, due to the Minisforum consuming massive amounts of power, all of the safe amount of amp hours that we could use batteries, even with sized down batteries for both robots, still came out to more weight than just using 2 batteries, one which includes the Minisforum. So in the end, we did decide to go with 1 battery for each robot, and the mini-bot's battery will just be also powering the Minisforum. And this is part research.
Yeah, this is a familiar slide because we're using pretty much all the exact same types of bulkheads from before. There's just going to be a different amount of them. Most of them change because of the Minisforum, so this time we're having 2 Ethernets instead of just 1 before. We have 1 battery, used to be 2, but we no longer have that aux battery. And yeah, pretty much the exact same.
For our mini box, we went with a 20-inch by 11-inch by 3-inch for the dimensions, and then our sheet metal thickness is the same as the main box at 0.0625 inches. We have 2 USB-A ports on opposite sides of each other, so one right here and then one right here. And then our 3 motor ports are currently over here. Our 2 D-subs are right there. 2 Ethernet ports are right here and then partially covered behind that wall right there. And then our battery and e-stop are currently on this wall, and then our camera mount poles are going to be right here.
Yeah, so speaking a little bit about this, the Minisforum added a little bit of complications for us, but mostly we're going to want to try and have a lot of our, so it isn't really told, but there's a camera around here. And so what we want to have is have these ports over here directly feeding into the Minisforum because they're not going to really be used for much else. So that was the intent behind these being directly over here. We can't have anything on this wall over here because it is blocked. But yeah. And here is our general overall layout. We have a lot more space on this one here.
Opening up the questions now. Very simple. Hi, Alex.
We can't have anything on that section of the block.
Okay, so it's not entirely blocked, but we don't really want to have anything on that side. Minisforum is very big, and we don't want to have wires moving around it. We could theoretically have some stuff there. It is what I want to say. It is not desired, optimal to have it there. We have so much more space around the other things. We can move stuff around that we would rather. We don't want to mess with the Minisforum in any way because it's very important.
Other questions?
Yes. That USB-A connector that you have listed to AC USB 3-AA is a one-port USB connector. I have the data. I'm looking at the data sheet for it right now. I don't know if you meant to put a different one on there.
We definitely did because it's not
great.
Yeah, the one we actually have listed in our bills of materials is definitely 2-port. I double checked that.
Okay.
Probably just the one.
Double check if your part numbers are consistent.
Yeah.
The one we have listed is definitely one.
Yeah, there should be 4 ports in total for software.
We got one from Slido, Anonymous. With the battery down to the end of the mirror deposit, large plant and harmful box. Are there any concerns compared to
Yeah, so again, battery was a bit of a concern, especially for Minibot. We weren't even sure if 16 amp hours would fit, but I do know Drivetrain and us were working on it. There were a few different solutions. Emily, there was one where we could potentially cut into the frame a little bit and have it there, right? And then
Which one, the aux battery or the other battery?
just the main battery.
The main battery is already in the frame.
Yeah.
And in our slides.
Yeah.
On the breakers, you have, you said you have 15 amp breakers per minute. What are those breakers power?
I would have to go all the way back. I apologize. To the breaker layout. I can't remember off the top of my head. Like I said, I would probably need the layout, but
Not like the actual wire, as literally what is connected downstream of them. Are you connecting the drivetrain motors downstream? Are you connecting the minis from them? What are they connected to?
yes, I believe if I'm remembering right, they were for the. I believe they were for the extra motors because I believe we're using more heavy duty motors on the Minibot due to it having to move around more, I believe.
Yes. When I asked for this on main one, you said linear actuators and the Jetson. One of those being the minis form of directly translate. Linear actuators don't have input for components. I would check.
Yeah, like I said, I do have to double check that.
I think I would also bring up again that I trust a lot of our trust motor controllers to be good at just saying, hey, we have tested extensively and they do trip and they do stop faster than your breakers can. And they trip reliably every time without any of the NEA issues, like tripping too early or not tripping enough. So I would trust the motor controllers to trip, to deal with themselves, and then everything else you can handle with breakers.
Yeah.
If we do end up using a different battery size, are the battery protection circuits able to handle different size batteries? Like, are we using the same one on both components?
Yeah, the battery protection circuit should be able to handle between the two batteries. Yeah, they're designed for that.
Okay, one last one from Slido, really fast. Any reason why T74 is next to breakers or TC on the other side? This is also from Anonymous.
Yeah.
I think That might be a holdover. So recently we were just given, I think 4 more inches to the actual overall width of the box. That I think is a holdover from the days where the Minisform was like completely blocking that side. We could move it around as well. That is definitely something we could look into.
Okay. It's like really good. Software.
All right, so for software, we're gonna start with our behavior for the mini robot.
Yep, so same story as the first chart. The green is what you might expect from like the system's ConOps if everything's going great. The red states are the failure states we're considering. Sort of similar story for traversal. We have different ideas we consider if we lose our path, if we stall, if we get stuck. Some of the other states, it's just, are we stuck, or are we stalling? We hope to handle that in all the different cases. This one's a little less complicated than the main robot just because it doesn't have to do all the excavation work as well, but yeah. For the link-up process, this is how the main and mini robot will interact while they're near each other. And the most crucial part is that while they're near or in range of touching each other, only one robot should be moving at a time. So what this chart is basically demonstrating, the green blocks are movement. You'll see that the main and mini robot never overlap in the times when they are moving, basically to align to each other and deposit into each other. They always have to wait for the other robot to signal, hey, I'm ready. So yeah, that's the basic idea of that. We want to avoid any complications that could arise from the 2 robots moving around each other.
In terms of camera mounts, we're gonna have 2 cameras that are gonna be mapping and a LiDAR. The cameras are gonna be, one's gonna be on the back, or one's gonna be on the back facing flat, that'll be looking at the April tag on main robot. And then the other camera is gonna be facing downwards on the front, and the LiDAR is also gonna be on the front. And it'll just be, LiDAR will just be mounted flat, and it has enough of a range to be able to see everything that we need to see.
Our simulator is now working. We can test pretty much the whole behavior in the simulator without needing either robot to be ready. It's capable of simulating the entire perception stack. It's not necessary to do that, but for testing, that's helpful. It also lets us demonstrate running all of our software at the same time without any 2 pieces like conflicting or overlapping, which was a concern.
That's it. Very short. Any questions? Will?
We have plans to use the 2-row simulation to have it on the path planning for excavation samples.
Yes, we will be using that as we get into more behavior style. Yes. Peter.
Another of the 2-row section, I'm going to ask about the LiDAR, which is, as you mentioned, we don't quite have it yet. So you already have mounting for the LiDAR planned?
Yes.
And there are holes that created for that on the box?
Yes.
Okay, good.
We will, there's documentation, this should fit well. Yeah. If it doesn't end up showing up, if we don't end up using it, then we do have cameras there already. We might want to add another camera for a little bit more visibility, but we will look into that when we get to that point. How's it going?
So on the behavior, it says that we're waiting for the paper line. So is only one robot making that alliance confirmation, or are you using the cameras on both robots to confirm that?
Yes, the main bot has an April tag that the mini bot's going to look at, and the mini bot's going to determine whether or not it's aligned. The main robot's going to get to the right location and stop, and then the mini bot's going to go and actually move up in a line to it, and then it's going to say when it's ready, and then the main bot will be able to then deposit into the mini bot. And there's enough of a clearance between the camera and the April tag that you can see that even when you're right up against it, so we should be good there.
Also, I'm not sure if this was in your section, but What's the actual control scheme for this, like in manual setting? Like, are you switching between them, or are you not two controllers? What's the?
Yeah, so the current plan is that we would have two controllers. We are able to control each of them individually. So we would have two controllers and we have three people in the control room. So one person would be working on each robot and the third person would just be there to manage the whole thing.
Got one in Slido. Any plans on testing bots in it, either like simultaneously or individually?
Yes, we definitely want to test both robots in every scenario we can. We're definitely going to want to look at when we get both robots, especially the initial moving out and disengaging maneuver with starting with the starting location because we're so space constrained in our starting location. And then otherwise we will be testing as much as we can in sand pits and in our test pit.
Another one from Slido, no one here has a question. Minibot is inoperably stuck, would it completely shut off to save power, or does it want to still run to operate the system?
I believe the current plan is that it will attempt to get itself unstuck at the beginning, and if it's unable to do that, it will stop. And at that point, we may consider that we would fully shut down some processes such that it wouldn't use as much power and go into a power saving mode. That would be something we could consider.
That one from Max. In the Slido, I'm on the Slido right now. Not all the rules work when only one robot can autonomous or points. Is that a possibility?
So I believe that if we are controlling either robot at any point, we will not be able to get autonomy points. So we will have to have both robots be fully autonomous, yes.
Well, how are we going about identifying whether or not it's stuck in the program?
So there's a few different ways to do this. One way would be if the wheels are moving, if we're like giving them a command and we're not seeing any difference in our odometry. That could be one method. That's kind of the most standard one. I mean, other ones, I guess we'd have to test, try to play around, try to break stuff. But yeah, that would kind of be an example.
The planner does have some stuff built in to ensure that we're making progress, so we can look at that for reference. Like that path.
Dogs?
I assume you have checked the angle on the angle that you have the camera so that the camera can always see the angle tag from any reasonable set of distances.
Yes, the camera will be able to see the input tag even when it's right up against it.
Great. I know the box size has changed. Has that been taken into account?
Yes, but the box size has changed, but that was counteracted by the fact that there's a flap.
Great.
So with those two, it's basically the same, and it would be good. And if we do, we can reduce it slightly, and we can reduce the input tag size slightly if we run into some issues.
One thing. So one is just valid link location found. Who finds it? Is that going to be us? Is that going to be the robot? How?
So the current plan is for Minibot. So once Minibot makes its way out of the initial area, it'll find the valid path out of like that initial excavation zone. And then the link up spot will be some location on that path that's the straightest line that can accommodate that 1.5 meters. That is our full configuration.
All right, will the sinkage and previously dumped tracks affect the lens?
It is possible. I don't see it being a significant issue as the tracks shouldn't sink as much, and the improved wheels also should not sink very much. We may need to add some code to make sure that we're not turning in that area so we don't sink us down as much. We'll see when we test it. That's it then. I think we're good.
Definitely got any more questions.
Okay. A couple more last little things before we're done. So upcoming deadlines and dates. February 4th, that is team photos and NASA media release due. If you are in the team photo, we would like a media release for you, so also you can be in like the roster and stuff, and we can tell NASA that you're here. STEM industry plan is due the 26th. That is a fun project for me and systems. We get to write out all the cool stuff we do and condense it to one single page of writing. And then the next big thing is March 20th is presentation and demonstration due. So for those of you who do not know what that is, that's basically we have a date with NASA and we tell them all about our robots and we hopefully show them part of our robot or a working robot or something about a robot. Also, this is not on the slide. Next meeting on Tuesday, if you're planning on skipping that and you do not have a reason that you have to skip that, please be there if at all possible. You're a new member, we have a lot of like little to-do list items such as joining Boiler Link. If you're a new or not new member from last semester. We also have a couple things. There's going to be an overview of the competition trip. We will go over NASA media release forms. You do need to do that, please. As well as BIDC compliance, access, safety, all of that fun stuff, quizzes. Alex has fun stuff about that. So please be there on Tuesday if you can. If you cannot, we will figure it out. But there's a lot of important stuff, so we would like you to be there. Aside from that, there's no slide after this. Thank you for being here. For everyone who joined online, thank you.